Hello and welcome to the second Eddy Cross Disciplinary Symposium. My name is Philip Judge. I'm a solar physicist at the National Center for Atmospheric Research in Boulder, Colorado, where this morning it's beautiful, sunny, a few clouds around, and it's going to be very warm. This is the second of the Eddy Symposia, the first of which happened 11 years ago, and we met as a group in Aspen, Colorado. And here is the advertisement that we put together for this particular meeting. As it shows, we met in October in the fall in Colorado, which is a lovely place to be at that time of year. Now, the picture shows John Eddy. You can see that, unfortunately, he passed away just before the meeting, but his family showed up and were very appreciative of this whole meeting. And John, or Jack Eddy, was a very remarkable guy. He was rather self-effacing. He would not brag about things. But while he was also at NCAR, and while he was there, he wrote this marvelous paper, which is in a little yellow box, on the Maunder minimum, where he says poetically, the reign of Louis XIV appears to have been a time of real anomaly in the behavior of the sun. And this particular paper, I believe, marks perhaps the beginning of modern research into the influence of the sun on the Earth. While I was lucky to be partaking in the first symposium, I was not so lucky as to ever meet Jack. He was at NCAR when he wrote that paper, where I currently am, but he was there in the 70s, and I was there later. But I can tell you that he would have been surprised and delighted to witness both of these meetings. This meeting is a little bit of an experiment because we haven't really tried this kind of multidisciplinary thing before. We've got some excellent speakers, we've got some wonderful posters, and we've got a lot of very interesting people tuning in for this meeting this week. If we have a measure of success, I would say it'll be a success if every participant enjoys it, if you can take an active part. And by this, I will refer to the Slido buttons that you see at the bottom of your screen, where you can ask a question and a moderator will help the speaker answer those questions. This is going to be a success if you can do this. It'll be a success if you discover new and interesting people. I'm sure that will be the case. You would, and maybe you discover new and interesting collaborative projects. This is a very important goal of this meeting. And finally, if you join a new collaborative group, we will be meeting on the final day to see if we can forge some new groups of people of mutual interest from different backgrounds. And also, if you can come to Vail, Colorado next year for the third Eddy Symposium, then we can take a look at what happened in the intervening 12 months. Now, it's my pleasure to introduce the person behind all this, Lika Guhatha-Kurta from NASA. And she would like to say just a few words about Jack and this particular meeting.
Thank you, Phil. That was wonderful. Kind of want to say, if you look at this graph, you can see how global this meeting is. I actually had to sit down and count how many countries. I think about 41, but I know Kendra knows the best. But it just shows the level of interest in this meeting. It's also because it is very different from the traditional meetings in different area of science that we have. Now, I was really fortunate to have known and then really work with Jack for the last 10 years of his life. He was actually a consultant in the Living with a Star program, where a lot of the sun climate research in Living with a Star began. He wrote a book, The Sun, the Earth, and Near Earth Space, to guide Sun-Earth system. And this book has now its second edition, and you're going to hear a little bit about it. It's a book without math and with Jack's beautiful language. And at the end, I would like to recap what his wife, Barbara Eddy, wrote back in 2009 when this book was published. For those of us who were blessed to know Jack, we will surely always remember his kind, gentle, soft-spoken, and dignified nature, as well as his magical sense of humor. And I was fortunate to know him. Thank you. Enjoy the meeting.
Thank you, Lika. So now it's my great pleasure to introduce our first presenter, Dr. Massimo Mascaro, who has a degree in computational neuroscience from Rome. He writes in his material that online that he's very passionate about AI and basically making life better. He is the technical director of applied AI at Google, and he's going to give us a big picture talk. And I don't think the picture gets any bigger than something like Google. So Massimo, it's your turn to speak, and I will let you know when you have 5 minutes left. Thank you.
Thank you so much. 1 second to share my slide. They're not coming up as normal. All right. Thanks so much, and nice to meet everyone. It's my big pleasure to be here. As was said, I have a background in physics. I'm really passionate about science, although my career brought me to artificial intelligence and neural networks. But I'm really kind of happy to talk about the intersection between my two passions, effectively. And really kind of what I would like to kind of describe today is there is a double interaction. I'll first actually start from talking a little bit about some of the greatest successes and some of the biggest trends that I see from my perspective around how AI is impacting science. But also I want to kind of follow up later about how the opposite is also happening and how science is actually affecting how we're thinking about some of our AI techniques in general. So one thing I would like to kind of start from is that, of course, AI and the general discipline of data science goes back a lot, and a lot of science is about data analysis. So there is nothing like particular kind of, it's hard to pinpoint about a particular date or a particular event that really said, okay, that's where kind of AI started being applied to science. But there are a lot of examples going back, a few years of things that have definitely kind of change a little bit the status quo. One of my favorite examples come from the medical kind of field where we at Google work on a number of AI algorithms to extract information, medical information from very cheap analysis. So these actually are, for example, retinopathy, and a number of diseases can be detected from cheaper analysis. In fact, one of the things that we have as really as a real target at Google is how can we use simpler sensors, for example, that are in smartphones or in very cheap hardware to help detect, for example, medical conditions. But the interesting thing about some of this early work, is that initially a lot of these AI applications were really things on a side, and then were quite far from the mainstream publication. This is an example where things really reached that level of maturity where prestigious peer-reviewed journals started kind of validating and publishing these techniques, something that I think is absolutely critical for science, and thus actually for application of AI to science. We can't just kind of follow different procedures than what have been kind of established over a long time. So this idea of validating and peer reviewing this kind of research is absolutely important, as is the importance of being able to replicate some of this research. A big trend in AI today in general, but in particular in AI applied to science, is the ability to share data sets, results, and code so that other labs, people, and researchers can also replicate the results. Moving a little forward in time, another example I wanted to give you is a pretty famous result, again, from Google AI, where we basically look at Kepler telescope data, and we applied AI techniques to try to detect exoplanets that may have been missed from the traditional analysis techniques. And this actually led to a discovery of a couple of solar systems that actually kind of have gone amiss in that particular data set. The interesting thing about this is that while those techniques were not particularly revolutionary for the time in which they took place in terms of an AI techniques, it really kind of spurred a lot of other research and other applications of the same analysis techniques from an AI perspective. And these, again, were deep learning models that actually kind of are becoming a little bit more of a standard. We at Google have been working with, for example, people from the TESS team to analyze data from the TESS telescope. So these actually are pretty early examples of applying modern AI techniques in a way that, again, is not revolutionary from an AI perspective, but actually is very, very impactful from a science perspective to detect patterns, to understand data in a much richer way. You may argue, though, that this is basically trying to kind of raise the human perception of this data and the human analysis to improve it. But it's not really transformative in that it's kind of changing the way in which you do science. But actually, things are improving even beyond that. One very recent example that probably you guys heard is AlphaFold, an algorithm, a deep learning algorithm from DeepMind, another Alphabet company that specifically does AI. Where they were basically trying to build actually machine learning system to predict the folding of proteins, starting basically from their amino acid structure. Those of you who do computational biology know that this actually is an extremely challenging problem, and is considered to be a very important problem if we want to get to a point where we understand life and we're able to engineer drugs in a much more sophisticated way. One thing actually about this kind of work is that, again, a lot of the mechanism and the research behind these algorithms gets published in peer-reviewed journals, in this case, Nature. And so it's available as a technique. It's not just Google trying to build a particular technology. It's really these sophisticated labs, AI labs, trying to contribute back to science techniques and tools that then can be used in many, many areas of science that actually are related to those kind of topics. One other thing actually I would mention here is that there is also a lot of research around making some of those models that very often when they come out as research model are absolutely enormous in terms of size and computation required to run them and train them, to make them smaller. And so this actually is another area of contribution that I can see AI working, because in a lot of applications, you just can't run gigantic models at all time. Again, think about medical devices or diagnostic. Think about, for example, running some of those algorithms on satellites that are in space to detect actually kind of scientific events. One thing, however, as I mentioned, that I'm really passionate about is that these actually are examples of applying AI techniques to science, but they really kind of don't leverage too much the science knowledge that we have built over centuries. In a sense, a lot of these algorithms that I've presented, they basically leverage the power of data. They sift through gigantic data sets of data. They use, again, these sophisticated pattern recognition techniques to extract information out of data, usually thanks to supervision, that is, thanks to labeled information that scientists provide the algorithms up front. But the process of science is not always that easy and that linear. Very often we are confronted with problems where we do not know the answer. And also very often we want to use and leverage the knowledge that we have accumulated about science, being physics, chemistry, astronomy, or whatnot, in order to make those algorithms smarter and not just having to reinvent, if you want, the wheel every time because we're just kind of starting from scratch from a data set. So this is actually is one area where research is still kind of very early, but we are seeing some initial example. And I'll kind of give you a couple. One example comes from effectively fluidodynamics, but really climate. I don't know how many of you work in this area, but I was very surprised to see how even state-of-the-art, kind of some of the largest simulations that NOAA runs still run at a pretty rough, if you want, discretization level. This is, of course, is the standard techniques that is mostly bounded not because of our lack of knowledge of how fluids or the atmosphere behaves. Very often, we know actually a lot of the physical laws that kind of govern those processes. But it really kind of comes down to data and computational issue. It's very hard to run computations in three-dimensional spaces with very, very refined discretization. And so we have to make approximation. And this, of course, eventually affects the way in which we are able to, in this case, for example, predict or model climate or weather. Now, a very interesting idea and techniques, and here I have a paper for you that you may want to kind of have a look at, can actually take the physics of the equation, but have the neural network now learn a better way of effectively approximating the operators, the local operators that I apply to this discretization. So the idea is that instead of using the traditional, finite difference, finite method techniques, they usually kind of tend to be, linear or second order. In the fancy cases, you get third order, but they're really kind of fairly simple approximation. Can I have an actual neural network work at each level of the grid and trying to predict what the grid cell is going to do based on its surrounding? So the interesting aspect here is that I'm not trying to detect a pattern across the global space and sifting through data. I'm trying to detect a pattern at the local level, and then I'm using the knowledge of physics of how all these cells cooperate together and what actually my, for example, partial differential equations are going to tell me of how the system evolves to effectively try to understand the evolution of the system as a whole. This is extremely interesting because, again, it's not throwing the baby with the bathwater. It's actually combining powerful AI techniques with our knowledge of physics and kind of taking the best of two. We have early results, some of those are in this paper, where we show how this actually can lead to a much, much faster simulation techniques than what traditionally you would do with traditional methods. This has been expanded even more. This actually is another group from DeepMind that has applied the same kind of reasoning and ideas, but by basically modeling, instead of like with discretization, with particle methods, some of these processes. And the nice thing about their work is that they also kind of did a number of simulations that are extremely visually appearing. So I'll show you some of them. So what you see on the left is basically a ground truth from a traditional CFD simulation. And what you see on the right is a prediction from these AI approximated models that effectively are approximating and trying to infer how the different particles are moving. And as you can see, I mean, like, while there are differences, and in the paper they are explored and explained in great details, the system is able to capture a lot of the physics with these particular techniques. And as I said, the promise of this method is that those simulations would require much less computation, that kind of really results in us being able to run much larger computations or much more accurate computation overall. So this actually has a lot of interesting aspect from a science perspective. Now, I want to switch gear and also kind of put on your mind another topic that is very dear to both me, my work, and actually kind of what I do at Google. This actually is a graph. The graph that you're seeing here is a graph of the requirement of AI computation of some of the most famous models of the last few years in deep learning. And as you can see, like, there is a linear scale for the year, but there is a logarithmic scale for the computation. And this, by the way, is absolutely not surprising because in a lot of like computational domains, we have these things called Moore's law, where effectively we know that computational capabilities and computational requirements are usually exponentially increasing. What is a bit stunning in this particular graph is that the rate of increase, so if you want the exponential trend here, is about 5 times faster than what normal computing does. It basically doubles every 3.5 months. And so it is very, very clear that with this rate of increase of AI computational demand, normal computational devices are not keeping up. There are already people that are discussing whether Moore's law is going to apply over the next few years as applied in the past, but this actually is much, much faster than Moore's law. So what are people doing about it, and why? How actually can this impact how AI and science work together? Well, for one thing, people are building a lot of accelerator, dedicated hardware for this particular kind of workloads, deep learning. And this hardware has proven to be extremely interesting also for scientific workloads. I'm pretty sure that all of you have worked and are very well aware of GPUs. But actually, much more is coming down the pipeline. We at Google have built...
Massimo,
Sorry?
5 minutes.
Yes.
5 minutes. Thank you.
Sure. I'm about to close. This hardware is that we have built at Google is dedicated for deep learning models. But the interesting thing, in my opinion, is that it's not the hardware itself, is the fact that this hardware is extremely scalable and made to work in parallel. So already today, for example, you can rent from us computers basically the size of supercomputers, like 100 petaflops. In fact, we just announced at Google I/O the availability of the V4 of the pods later this year, that will actually reach 1 exaflop in a single computer. And the interesting thing is that you can rent this kind of hardware from us. Now, it is true that this is hardware mostly dedicated for deep learning, but actually we're seeing some groups doing work on this particular kind of machines for example, kind of scientific purposes, either because they use AI within science or for more traditional AI science simulations themselves. So definitely kind of a trend to keep an eye on, and definitely another area where AI and science will interact together. I'd like to conclude with a little bit of a shout out of some work we have been doing in the recent few years, us from Google with both NASA and the SETI Institute as part of this accelerator that is called the Frontier Development Lab. Again, for those of you who are maybe early career, this may be particularly interesting. This is another thing that I'm really passionate about, that is kind of trying to mix different expertise. And so what FDL really does is it tries to put together researchers, sometimes from Google, from also other institutions in AI, with actual scientists that work, for example, on space and exploration problems, and they work on kind of climate problems and a lot of like other scientific topics. And actually, this kind of interaction has led to a lot of like really, really interesting work that have been kind of published recently. So again, have a look at it. There will be a talk on Wednesday specifically on this by Sarah Jennings. So also have a look at her talk actually for more information about this. So that's all I have. I'll be happy to kind of take some questions on some of those topics and more. But yeah, very, very happy to kind of be here, and I really wish you a great conference.
Thank you so much, Massimo. Fantastically interesting career you have, and I personally would love to thank you so much for joining us today. So I'll pass it over to Dan Marsh. While I'm chairing the session, we also have a moderator for each session who is going to help with questions through Slido. This very general talk is just fascinating, and I wonder if if we do have any questions right now, over to you, Daniel.
Hello, everyone. Yeah, we have a few questions in the Slido chat. The first one is, how does quantum computing, how will quantum computing change AI computation time trend?
Very interesting question. So as you know, first of all, I mean, like, I want to kind of prefix that quantum computing is still very early. We're still trying to kind of make quantum computing doing anything useful. So like, you know, kind of let alone things that are sophisticated. That said, two things actually kind of I'll just kind of tell you very quickly. First of all, there are a lot of at least both theoretical algorithms and people working on where basically quantum computers are used for generic optimization problems, right? Where you're basically trying to find minimum of particular kind of surfaces. Deep learning is exquisitely a minimization problem because very often you're trying to minimize a particular loss in order to find the right weights of a particular neural network. So that's actually the simplest way of like using quantum computer neural networks. There is a more complex way where you can actually build neural network that have, instead of normal weights, they have effectively quantum weights. And this opens up a lot of possibilities in terms of this network doing things in a much more efficient way, because now each weight doesn't hold just one value, but effectively a superposition of values. And this, again, is something that we are researching at Google. There are a lot of other labs around the world. But just to be clear, like this is actually still quite far from application because the current physical machines that are available, including the ones at Google, are still very far from the kind of computational power that you need to experiment on this.
Great, thanks for that. Next questions come through is, can you speak to the potential of graph representation in AI?
Yeah, no, it's very very important. Maybe I haven't emphasized that enough, but the work that I showed here by the Bataya group is actually based on graph neural networks. That is an emerging techniques where, as you kind of were pointing out, graph are used and relationship between things are used. Of course, this is a particular application of graph networks, but you know, there are many others. And just to be clear, there are also others in domains different from the application directly to physical systems. But yeah, this actually is absolutely kind of one of the biggest trends that I see in the last couple of years in deep learning, and it's actually of paramount importance.
Okay, great. Interesting. So just trying to find the next question here. So what is the next milestone we need in machine learning?
But that actually kind of, now I'll go completely kind of on my personal opinions, because of course, like everyone will say his own one. I think that, you know, I think actually kind of this talk actually probably give that away. I think actually the meshing of pre-existing, if you want, kind of deductive content with inference is the biggest kind of holy grail. In a sense, we went from AI systems that were particularly kind of, if you want, based on kind of expert systems and deductions. That was actually the kind of AI that we were doing in the 70s and the 80s. To this world of deep learning, where it's really the emphasis is on inference and pattern recognition from data. But I think actually kind of the real holy grail will be at the intersection of those two. And, you know, although I presented some examples of research going in this way, I think actually there is still a lot of like development that have to be created in terms of kind of making that really seamless and super powerful as kind of we would like. But I think actually that's really where we'll start kind of reaping actually the most benefit from both our, again, centuries of accumulating knowledge, not just in science, but in any area, and the ability to sift through massive data sets and extracting complex patterns.
Okay. I have a question concerning the point you made about relatively coarse resolution for weather models. So what spatial resolution can AI reach with the hurricane simulation you mentioned? That's from Hanley Liu.
Yeah, so there is actually kind of work done on not specifically hurricane simulations, but on local weather prediction, where they actually show about a 10x improvement in some of those simulations. Now, keep in mind that, and this actually is one important point, the scaling of the simulation, I think I have it in the previous slide. Yeah, the scaling of the simulations goes as basically the discretization factor to the power of d+1, right? This is the number of dimensions. So when you do work as some of these papers do in 2 dimensions, you usually get actually kind of a cube of the distribution factor. So let's say you can shrink your grid by a factor, let's say 2. So like you can kind of work on a grid that is twice as big as like what you would normally do in your simulation. Then you get actually a speed up of about 8, that is around a factor 10. But like as you go to 3 dimension, that actually becomes immediately 16. And if you can kind of make these models more powerful, and some of these papers are getting close to a factor 5 in terms of kind of the grid scaling, now you start having 2 or 3 orders of magnitude in terms of how much actually you can speed up the simulations. And this is really kind of the difference between running a simulations on a supercomputer and running it on much kind of common hardware, right? And so this is why this actually could become very transformative. Now again, I mean, although the picture is for a hurricane, a lot of the work here has not been specifically on hurricane, at least that I know about. But you know, like the interesting results so far on local weather prediction are really pointing in this direction of like this scaling factor are really working, and you can actually get 1 or 2 orders of magnitude at least when you run those simulations at scale.
Thank you. I see Phil is back on, and we have to move on to the next speaker. So yep.
Indeed,
okay.
yes. Thank you, Dan, and thank you so much.
Thank you very much.
Massimo.
Thank you, everyone.
I encourage those young people who might be interested to reach out to any of our speakers. Not so young people are also welcome, of course. And I just thank Massimo once again. And we move on to our next speaker, who in the field of solar physics is known to be one of the modern day giants. Peter Foucault has a PhD in astrophysics from Manchester University in the UK, not too far from where I'm from actually. And anyway, he is one of the best known solar physicists. He's also known as a kind of Renaissance man in the sense that he's got very broad interests. He's an author of a variety of different kinds of books, multi-talented. He started his own research organization in Massachusetts many years ago and was in charge of that. It's focusing on instrumentation for solar physics. And today, as you can tell, his breadth is going to be reflected in the title of his talk, which is Some Thoughts on Future Directions for Solar and Sun Climate Research, followed by a discussion. And Peter, after about 40 minutes, I will flag that we should get ready for some questions, and then Dan will intervene. So welcome, Peter, and thank you so much for joining us today.
Thank you, Phil. I would like to thank you and the organizing committee for inviting me to give this presentation. Jack and I were longtime friends, and I value very much the mentoring that he provided for my early career, and also for that of a number of other astronomers of our generation. So the next slide, I would like to go into probably the main areas, listing the main areas where solar studies have impacted on other disciplines, and vice versa in a symbiotic sense. These cross-disciplinary interactions are usually in 2 directions. So the first of these is the study of possible variable solar impacts on climate. And that's the area where, of course, Jack made such a large impact. He, in fact, made that field respectable, as Phil alluded to previously. And then there's the area of transfer of insights between the sun and similar stars. This is a very fruitful field that was developed largely through the pioneering work of Owen Wilson at Mount Wilson in the 1960s, and has turned out to be a very interesting source of understanding. Then there's the learning from analogies to laboratory plasmas, which takes us back probably to the 1940s when Hannes Alfvén pretty much invented magnetohydrodynamics. And then T.G. Cowling, amongst others, applied it to both laboratory, but also to most notably the solar physics. And then there's the vast area of solar terrestrial studies, which has to do with the variable solar effects on magnetosphere, upper atmosphere. There are many practical applications to telecommunications and power line disruptions, and the kind of work that probably Lika might agree probably underlies much of the NASA interest in solar physics these days. So the next slide shows that that our man Jack was a thoroughly cross-disciplinary man, and you can see on the left a picture which where he's linking arms with other cross-disciplinary individuals, like the eminent climatologist on the left, Jerry North, who I think perhaps is participating in this meeting, and the expert on tree rings, Chuck Stockton from University of Arizona. And then over in the far right is Marv Geller, who's a noted fluid dynamicist expert in the atmospheric dynamics. And the gentleman between Marv and Jack is a Lithuanian host of ours at a very interesting panel that was held between United States and Soviet bloc scientists in Vilnius, Lithuania in 1981. And you can see that, or rather, the symbolism of this picture is that we are not only crossing disciplinary boundaries by linking arms there, but we are also standing on the Polish-Lithuanian border, and we are transcending national boundaries as well. So in the late 1970s and early 80s, Jack Eddy was one of the most famous astronomers on Earth, right up there with Stephen Hawking and with Carl Sagan. And Jack once noted to me with a wink that he knows he's made it, that he's famous because his work was covered in TV Guide. Now, TV Guide at that time was in fact the largest circulation publication in the Western Hemisphere, perhaps on the planet. And so this is sort of probably the closest simile to that for those of you who are too young to even know what TV Guide was like having your scientific work featured on Fox News. So the next slide shows what made Jack notable. And you know, it wasn't only the fact that Jack became famous. Perhaps what's more important is that it drew the attention of millions of people to solar research. At that time, Hal Zirin, who was a professor of astrophysics at Caltech, told me that Jack's 1976 paper in Science that discussed the Maunder minimum doubled the enrollment in his class on solar research. So that was one of the impacts that Jack had on the field in general. So what was it that Jack did that was so notable? Well, here in the left panel, you see a plot of the sunspot number going back to the beginning of telescopic measurements. And you can see that the sunspot number goes up and down, the blue line, pretty much regularly around 11-year cycle. But back in the middle of the 17th century and early 18th century, the sunspots went away for about 75 years. And that was known 100 years before Jack got back to that topic. But he bolstered the evidence for a great reduction in the magnetic activity of the sun by using carbon-14 radionuclide evidence, and also measurements of or records of the aurora going back to the beginning of the millennium, and also records of naked eye sunspots, which include Chinese records going back about the same stretch of time. So he made it much more believable that the sun sort of went away on us magnetically for quite a long time, and set a lot of people thinking as to what might have caused that, what its implications might have been. And so Jack also drew the connection between that Maunder minimum of solar activity and the so-called Little Ice Age, which you see illustrated on the right in a painting by Bruegel. It was an extended period of the greatest cold in the Western Hemisphere, perhaps globally. And again, that was a connection that had been made previously, but Jack bolstered it with the latest evidence from tree ring data and corals and stuff of that kind. So that's the next slide shows what Jack's ideas, which have turned out to be pretty much borne out by later evidence, translated into when people looked at some of these things in a different way and perhaps more quantitatively. And this is a plot that was made by the climatologist Tom Wigley for a paper in Nature that we wrote in 2006, a review paper. And it shows the black line is a reconstruction of the Northern Hemisphere temperatures going back through the last millennium from paleo data, which I don't pretend to understand, but Tom does. Tree rings and corals and things of that sort. And plotted along with that are two curves, each of which shares the same volcanic forcing and the same anthropogenic forcing, but they differ in their solar forcing. The solar forcing there is based on modeling of what the total solar irradiance at the top of the atmosphere might have been during that period of time, and is put in there in two formats. One is what you would call a conservative estimate, and the other one would be an enhanced estimate. I'll get back to what that means in a moment. But the basic point is that the conservative estimate really produces very little signal in the global temperature, but the enhanced one might account for about a third of the temperature, global temperature variance over the past millennium. So that's fairly significant. And the next slide shows, for those of you who are not solar dermatologists, students of all the structures in the sun, the magnetic structures that I'll be referring to that cause total solar irradiance are, first of all, there's the dark sunspots, which you're all familiar with, and they cause a drop in the solar luminosity, although the reason for this drop is a lot more subtle and interesting, and I'll get back to that later than you might think. And then there's the increase of the TSI by the bright active region faculae that you see on the top. And then besides that, those two components of the irradiance variation of the sun come and go on timescales of days to months, and also over the 11-year cycle. Now, the third component is the contribution to the TSI by the so-called quiet network, which covers the whole sun. And you can see it reasonably well here, but it's everywhere. It's a sort of a polygonal pattern. And that's considered to set the baseline of what the total solar irradiance is on a longer timescales. So on the next slide, so armed with that information, you can sally forth into interpretation of this next slide, which the top panel, the blue curve shows the standard solar model. This is the TSI variation produced by the coming and going of the magnetic faculae and the dark sunspots. And the red line shows what happens if you add into that the removal of this quiet network, all those little tiny blopos that you saw. If you were to take those away, and we're not really sure that's ever happened, but if you did, the TSI variation would be a whole lot bigger, about a factor of 3 or 4. And that's about the amount you would need to make an impression on the global temperature as shown in that earlier slide. And you can see that in the lower panel, it shows you that if you focus now, you don't have any of the volcanic stuff in there, and you don't have the anthropogenic influence either. The global temperature response to this enhanced TSI variation is quite significant. It's the red curve that you see down at the bottom. It's about a 1/4 of a degree, and that's about a third of the excursion in global temperature, the warming of the Earth since the modern minimum that was obtained from that reconstruction that I showed you from the paleo data. So the next slide, I think we're missing a slide there. There we go. So to distinguish between these two models and to go further in identifying whether in fact climate might be forced by solar luminosity variation, the most straightforward way of going about it is you fly radiometers in space, and that's been done since the early 1980s, and you can see a tracing of that in the panel on the right. You can see there's a whole lot of noise in that. That's not instrumental noise. That the instrumental noise is negligible. Those are all ups and downs of the sunspots and the faculae, and they go up and down the 11-year cycle also. But you can see that at the solar minima, there are differences in the amplitude of the solar minima between the times when the sun is active or inactive rather, every 11 years. And much has been made of whether there's possibly a secular trend. But the problem is the radiometers themselves are not completely reproducible in time. It's very difficult to build a radiometer that is able to withstand the harsh UV and X-ray environment in space, and for a number of other reasons, there are drifts in the system. But luckily, on the left-hand side, the panel shows a new development in radiometry, the cryogenic radiometers, which are operated at liquid helium temperatures, and they're used by national standards labs as the standards of light flux these days. And those are about 10 times more accurate than the radiometers that have flown in space over the last several cycles. So looking into the future in terms of opportunities for the next generation, one could foresee, for instance, flying one of these cryogenic radiometers on the space station and calibrating the measurements of the sun taken at the minima, which is where you want to see whether there's a secular trend or not. You really don't care about the 11-year variation anymore. We understand that pretty well, but it's the secular trends that you're after. And the cryogenic radiometers offer some hope that we would have a stable standard to measure against. So the next slide shows that there are other more devious ways of getting at what the irradiance variation between now and the modern min might have been. And one of them is illustrated here in the panel on the right. You see that if you plot the radiative flux of these bright photospheric faculae that I showed you the picture of, if you plot them against the size of the structure, essentially it's magnetic flux, you can see, surprisingly enough, this is only something that came up in the last dozen years or so, that the small structures are the brightest. And that has a very interesting implication that if you start removing magnetic flux from the sun, you remove the sunspots and you remove the big faculae, and then you get to the condition of a quiet sun every 11 years. And then you keep on going, you start removing even the quiet network. Each time you remove a smaller structure, you're doing more damage to the TSI than if you had removed an equal area of the large structures. And that's something that's probably not quite filtered down to a lot of the modeling, but it's something that has been demonstrated quite incontrovertibly over the last 10 or 15 years. But the plot you see on the right was made at a single monochromatic wavelength, and really to match it up against the solar luminosity or the TSI, you have to have a measurement like that, either at many wavelengths or more elegantly to do it with a detector that has completely broadband response the way the spaceborne radiometers do. So in the next slide, we see that there actually has been an instrument like that developed and flown on balloons several times, and it actually using a modification of a fancy DOD detector, it is able to image with reasonably good angular resolution in the same integrated light that NASA periodiometers measure the total light from the sun in. So on the right panel, you see one of the first pictures of the sun in total light. You can see the bright faculae. But you can also see that if you're trying to measure what happens in the quiet network, that the angular resolution isn't really quite high enough. So this is the next opportunity I want to mention for the future in the next slide. Next slide, please. This is a picture on the right, which is not made with the SBI. It was made with a much higher angular resolution optical telescope, but it shows the kind of resolution you probably want to achieve with a next generation solar bolometric imager. That would enable you to evaluate what removal of the network would do if it occurs to the solar luminosity. And so a balloon reflight of the SBI modified to increase the image scale, for which the design already exists at Johns Hopkins University, would be something that'd be relatively easy to do and quite a powerful tool for understanding how the solar luminosity might affect climate. So the next slide addresses the issue of, so far we've been talking about TSI variation from magnetic structures, but you might ask, well, could TSI variation happen for other reasons than just coming and going of magnetic structures? And for 40 years, many of us have struggled with that, and there have been many observations of photospheric photometry, and nothing has cropped up. No, there has been no detection of any non-magnetic heat flux variations manifesting themselves as variations in the brightness distribution in the photosphere. Now, that requires some understanding, because if you think about it, the sun is this huge sphere, this huge cauldron of convecting, bubbling plasma. And it's hard to believe that the distribution of heat flow amongst the various eddies would be so stable that down to the level of sub-10%, that there wouldn't be any fluctuations in this heat flux. But the reason for this actually turned out to be very interesting, and it came out of attempts to understand why sunspots actually change the luminosity of the sun. The fact is that if you put a thermal plug into a pot of boiling water, you'll find that after a very short time that the heat flow will readjust around the plug, and the amount of heat coming through the top of the boiling pot will not have changed at all. So why is it that putting a thermal plug, which is what a sunspot is, into the photosphere causes a dip in the luminosity? And we know it does because the space radiometers have been showing that. So the answer is that when we were doing thermal modeling of this effect back in the early 1980s, that the result was quite anti-intuitive, that the insertion of a thermal plug actually has propagation of the isotherms back down into the convection zone of the sun, which is about 200,000 kilometers in depth. And it redistributes laterally, globally around the sun on a very short time scale. So the heat is being stored throughout the convection zone on time scales of a few days. But the time taken for this heat that's stored to re-radiate back into space is extremely long, so the order of 100,000 years. So you have this very interesting situation where a star like the sun is actually an incredibly good storage mechanism for temperature perturbations. If it weren't, you wouldn't see TSI variations at all. So that sort of helped to understand why it is that we don't see all this bubbling and so on, causing an impact on solar luminosity. So the next slide shows that still, science is never at its best saying what cannot happen. It's really, its strength is explaining what does happen or what is observed to happen. So surprises are possible since, for instance, we don't even know the scale of the convection responsible for heat flow to the photosphere. That's amazing after all this effort that's been put into understanding the sun, that something as basic as that is still unknown. So for instance, back in the 1950s, a polygonal velocity pattern of horizontal velocities was discovered, and you can see those on the right-hand side. This is a Dopplergram. So you're only sensitive to line of sight velocities. And since the velocities in the sun in the supergranulation are horizontal, you don't see them at disk center. But we still don't understand whether this polygonal velocity pattern, which is about 30,000 kilometers in extent, whether it's convection or whether it's perhaps a shear instability in the upper layers of the sun, where we know that there's a gradient in angular rotation speed. And in fact, it turns out that the faster rotation rate of photospheric magnetic fields, which is observed to be that the sunspots are actually plowing through the photospheric gas at a few hundred meters per second, so about 5% faster than the photospheric gas in general. And it looks like that the flux tubes themselves are very intense magnetic flux tubes, and so they rotate essentially as rigid spokes, whereas the gas goes up and down, conserves angular momentum. And so when it gets to the surface, it's going about 5% slower than the rigid spokes. So that would indicate that the interpretation of supergranulation, it's substantial, or it supports the view that it's actually a shear layer, and it perhaps doesn't carry heat at all. But the next slide shows, addresses this question of whether supergranular flow really does carry heat to the surface of the sun, or whether it's isentropic. And an interesting technique that, again, offers some opportunities for the future, it could be exploited more than it has, is that if you image the sun in the sum of two wavelengths that are the sum of two widely separated wavelengths, perhaps in the blue and the near infrared, you get a conventional picture of just the granulation. There's nothing very much going on. But then if you difference these two images, you actually are measuring the temperature gradient in the photosphere. You're no longer measuring the brightness temperature. You're measuring the radial temperature gradient now. And that's because the two wavelengths penetrate to two different depths in the photosphere that are separated by about 35 and 40 kilometers. And so all of a sudden, lo and behold, what was featureless in the sum of the wavelengths in the difference exhibits this pattern of dark structures, which if you compare it to a magnetogram down below, which is a little bit confusing because the magnetogram shows the two different polarities of magnetic field as different colors, as black and white rather. But you can convince yourself that these structures all map into the magnetic structures rather well. And that's interesting because it's a fact of modeling of magnetic structures, the faculae and the network, that the models all predict that there's a lower temperature gradient in those structures. And this technique that I'm describing to you is able to pick up this temperature gradient directly. So that gives you an opportunity to go back to the question of whether the supergranulation carries heat or not, because if there were changes in the brightness due to a greater efficiency of convection, the temperature gradient, for instance, should be higher, not lower. So it gives you a diagnostic that is able to distinguish between these two. And this is something that could be applied to much higher resolution studies using 4-meter telescope that's just coming online on Heliophysics, the DKIS telescope, or the one at Big Bear, or even the more modest precision solar photometric telescopes that we put into use back in the 1990s. So the next slide shows another diagnostic, which is that it's interesting to look at the photosphere, not only in visible wavelengths, but you can learn about convective heat transport also by a high resolution near IR imaging at 1.6 microns. And what's special about 1.6 microns is that you're looking at the point in the spectrum where the opacity of the solar photosphere is lowest. So you're looking at the deepest photospheric layers. And you can see in the panel on the right is a picture of a piece of the photosphere. It doesn't really show very much except a couple of small sunspots. But that same scene, when it's viewed at 1.6 microns, shows all these magnetic flux tubes, which when you look at them deeper down, they're all tiny, they're all mini sunspots. So again, if you apply this to the higher angular resolution available through the big solar telescopes that are being put online now, this could be quite an interesting way of studying heat flow below the layer, or at least somewhat deeper into the layer where the granulation, not the supergranulation, but the granulation, which is this turbulent convective, or the turbulent phenomenon that is right at the photospheric layer, which tends to smear out horizontal gradients in brightness temperature. If you can look through that layer somewhat, you might be able to spot heat flow variations that are of interest to solar luminosity studies. So in the next slide, so far all I've talked about is what the TSI behaves like at the lowest activity levels during the moderate minimum. But if we look into the sun's behavior, the luminosity behavior at the highest activity levels, we find something very interesting. So on the left-hand side over here, you see, once again, the TSI measure over the last 40 years or so from using space radiometers. And the bottom curve is the sunspot number. And you can see that when the sun is more active, it's brighter. But the caution there is that all those solar cycles that we've been observing with or during over the past 40 years or so were all of moderate amplitude. They weren't really the big guys. So if we look at the next slide, it turns out that the recent evidence actually shows that the sun does not keep on getting brighter with higher activity level. It actually dims at its highest activity levels. And that was shown in plots that this one was made by Sami Solanki and his co-workers at the Max Planck in Germany. This was published already about 30 years ago, and showed that if you took the space radiometer data, the daily data now, so that showed excursions of daily activity, which are larger than you see in the annual means. If you plot those against the sunspot number, basically the activity level of the sun, you see the sun does get brighter and brighter until you get to moderate activity levels, but then it starts getting dimmer. And the reason for that, it turned out after a bit more thought, is that if you look at the way in which the area of bright faculae behaves, it actually decreases in the two biggest solar cycles in recorded history, the ones that peaked out in 1947, around 1947, around 1957, although the sunspot area keeps on increasing. So the sunspot area is the dashed curve, and the solid curve is the faculae. So what happens there is that you're seeing a tilt in the balance between bright and dark structures in the sun. And that tilt is causing the sun to get dimmer instead of brighter. So the next slide shows the impact on that of that on a TSI model. So if you reconstruct the TSI using faculae, it shows, as you might expect from what I've just told you, that cycles 18 and 19, the really big ones, the sun was actually dimming. So in the 1940s and 50s. And then when you, in the lower panel, you see that if you do an 11-year smooth of the two TSI models, the standard model, which is the one that's in the dashed curve on the upper panel, and you 11-year smooth that, and then you 11-year smooth also the model that's based on the faculae, the one that's shown in solid on the top panel. You'll find that the model that uses the faculae, the one that shows the dimming in those two cycles, actually matches the global temperature variation that goes back to 1920 in this particular plot, somewhat better. than the standard model does. So that was kind of interesting also, and that shows some directions for the future and the recognition of this dimming effect is something that's worth thinking about from the point of view of climate impact. So the next slide shows some of the opportunities that what I've just told you present in stellar studies and climate, and also perhaps in astrobiology studies. So to sum up what I've just been saying, the sun appears to be unusual in that it's poised on the boundary between stars that brighten and those that dim with increasing activity. And on this slide on the right, or this panel on the right, you can see that these are stars that are roughly similar to the sun in temperature and in mass. And they're plotted with an increasing activity level along the y-axis upwards, and according to their temperature on the x-axis. And the sun is the one, if you got good eyes, you can see it's a circle with a little dot in the middle. It's about halfway down. And the stars that brighten with activity are the ones that are plotted as dark circles, and the ones that darken with activity are all the other ones in the open circles. And you can see that the sun is sitting pretty much at the boundary with respect to the activity level, the boundary level between those two species of stars. So we're presented with this interesting discovery, which is hot off the press pretty much, that regardless of whether the sun is going to get less active or more active, it's going to dim on us. And so it will tend to offset global warming to the extent that the luminosity drives global temperature, to what extent it drives global temperature. Regardless of whether it gets more active or less, it's going to tend to offset global warming. So that's one thing to ponder. The other thing to ponder is that the solar UV and X-ray fluxes are in proportion to the total magnetic flux in the sun, not just to the difference between the bright and the dark structures. They increase in proportion to the total area of not only the bright faculae network, but also the dark sunspots. So for instance, if you look at the sunspots in the range of plasma temperatures in the so-called transition region between the tens of thousands and hundreds of thousands of degrees, you find that, amazingly enough, we already found this out from Skylab back in the 1970s, sunspots are not the darkest structures in the sun, they're the brightest structures. So the solar UV and X-ray fluxes increase over the full range of activity. So this dichotomy that you have, that the sun gets dimmer in total light, but it continues to get brighter in UV and X-ray if it gets more active, is something that I don't think anybody's really thinking about yet, and it might have interesting astrobiological significance for explaining life on Earth. I say this as someone who knows absolutely nothing about astrobiology, but I'm just tossing that out there. So the next slide shows a situation that I can't resist mentioning, because it's sort of a poster child for cross-disciplinary studies. A few years ago, the Kepler mission that Massimo alluded to before observed hundreds of thousands of stars for their variations in brightness, but observed an F star that was dimming by several percent over the days and weeks. And there was no blocking that anybody could figure out by planets or spots. So there was a huge hue and cry about where's the missing rate of flux. And there was an editorial even in Sky and Telescope, have aliens build huge structures around the Pleiadian star. They were talking about Dyson spheres and about little green men. It was just a total media circus. But on closer examination, it was suggested that the the convective heat flow disruption, which could have been just caused by rearrangement of convective efficiency, for instance, could easily be stored inside the star in a way that the stellar physicists who were so busy working on the star had overlooked. And so probably the explanation of this whole thing, which is the most mundane and therefore has been resisted most by the media, is probably the one that fits the observations best right now. And so I think it's an interesting application of what we learned about the sun to the broader cosmos. Now, the next slide, in case you're not asleep yet, I'm just going to do one more venture into cross-disciplinary activities, and I'm going to go over into laboratory plasma physics now. So, for decades now, people have been admiring the beautiful structures in the corona. Over here is a picture from the Solar Dynamics Observatory of these 100,000 or more kilometer size loops that extend from the solar surface into the corona. These are structures that are millions of degrees in temperature, and their reconfigurations and changes in geometry and so on have been suggested to be those that would be brought about by reconnection. And so there's a vast literature on reconnection in solar research. But the fact is that the only physical observation that can prove reconnection is to measure the electric field that's predicted. And it turns out that measurement of the motional electric fields using Stark effect, the kind of electric fields that we're talking about here, is actually a fairly standard plasma diagnostic in tokamaks. It's been around for decades, but somehow it hasn't really made any impression on solar physics, which is focused more on measuring magnetic fields all the time. So here again, we have an interesting opportunity. And I'm just going to show a couple more slides related to this. The next slide, here is the kind of observations that can help discriminate between basic models of flares and prominences, between current interruption models and reconnection models of flares, and reconnection models of prominences, and ideal MHD. Am I running short on time at this point, or?
You're doing fine, Peter. You have another few minutes.
All right, I was told you'd stop me at 40 minutes. So these models are, these are some of the most, these models preoccupy a large fraction of what goes on in solar physics these days. And so there's great importance in using this electric field diagnostic to try to move ahead on problems that have been baffling solar physicists now for decades, with not a whole lot of progress. So the next slide shows that the electric field measurements would actually require only minor modifications to existing polarimeters on, for instance, the DKISS telescope, the big 4 meter on Heliophysics. And the panel on the left shows that the kind of electric fields that are expected from reconnection produce a pretty large modulation of a high hydrogen line, something that would be easy to detect with a modern polarimeter. And the right-hand side is a schematic of a very pioneering, very primitive, really, electrograph that we designed and built on the Evans chronograph at Sac Peak and operated for a few years. And there were some tantalizing detections, but the technology of polarimetry has advanced so much since this instrument was built that it would be very exciting to try that out on the DKISS, for instance. So my last slide is sort of a look into the future on a broader basis. I think that we all agree that we have wonderful facilities, both in space, where I think they're, according to what Lika has told me in the past, that we have something like 17 or 18 spacecraft to take measurements that are useful for solar physics. And then, of course, we have this wonderful 4 meter telescope coming up in Heliophysics and so on. But our paradigm for building such structures tends to be that we build the structure something similar to what's been built before, but bigger. And then after that, we go to the community and ask people, what do you think you can do with this? And the problem with that, in part, is that the country has a $23 trillion national debt right now. And building bigger and bigger facilities really doesn't have much of a future. And so we may want to consider that perhaps we're departing too much from the way physics used to be done in traditionally, which is to identify specific questions and then ask yourself, what specific tools do you need to answer them? And over here in the right panel, we have an example of what I'm getting at there. That this is a cutaway diagram of the Akron radiometer, which is the one that back in 1981 first demonstrated that the sun's luminosity changes. That was a problem that had been around for a couple of hundred years. And this instrument, which cost probably $5 million to design and build and fly, answered that classic question, and probably has done more for understanding of sun climate relationships than anything else that we've done on much larger scales. So I think that's my parting comment, is that looking into the future, our strategy for how we go about carrying out solar research could use maybe a little bit of a dusting off and new look. Thank you very much for allowing me this time for this presentation. My wife told me that inviting me to speak for an hour on anything I want to talk about is very dangerous. And I hope it hasn't been without useful effect.
Thank you so much, Peter. Lots of interesting things to think about from the point of view of a solar physicist. Some provocative things. Those that perhaps aren't familiar with solar physics may be surprised to hear that we have some really fundamental problems still in studying the sun, but that's the fact right now. Anyway, I'm going to hand it over to my colleague Dan, and he is going to present Peter with some questions, I believe. Thank you, Peter.
Thanks, Phil, and thanks, Peter, for a great talk. So we have a few questions in Slido, and I would encourage everyone, I know we have a lot of people watching online, to post questions and also to use the voting feature in Slido to promote ones that you would really like to hear answers to. So the first question we have is, you started your own research institute. How did you organize people to conduct frontier research? What is required to create a new environment for discovery?
Well, that's an interesting question, because I'm one of the few people in my generation who decided to not join a large research entity, and in fact set up a small company where we combined both pure research and also building commercial instruments. And there was a symbiotic relationship between these two activities. And you know, it was very instructive and very challenging at times. But I think that you know, it's something that I can't recommend it to everyone. I think that it can be quite stressful being an entrepreneur in science, but there are quite a few people out there who don't necessarily go for PhDs, who were quite willing to join a company such as ours, and who were able to do outstanding research. So I think it's a paradigm that I have written about in Physics Today, and tried to persuade young scientists to think more seriously about combining doing pure research with applied technology. But I can't say it's something that's really caught on very much.
Okay, thanks. The next question we have is, faculty area and sunspot area look like they increase hand in hand up to a certain magnitude of solar activity, and they then diverge. What causes this?
Well, that's one of the things that we need to look into more in the future. The the basic fact is that we don't have a widely accepted dynamo model of what causes solar magnetic fields and the oscillation of the 11-year cycle and so on. And in particular, we don't have a detailed enough dynamo to address the question of what is the size distribution of magnetic fields that are generated as a function of efficiency of the dynamo. I've consulted with dynamo experts on this issue over the years, and they all smile and say, we're not there yet. So that's the short answer to your question.
Okay. All right. Next question is, so we have interesting non-magnetic TSI variations are seen on the order of long time scales. Does TSI change due to any planetary differential gravitational influence, e.g. due to Jupiter?
That's also a topic that has been batted around for a long time. But I don't think it's an issue that we can discuss profitably here and now. I know there are some people who believe that such influences do exist, but I don't think that a mechanism with sufficient amplitude has really been widely accepted at this point.
All right. A question here from Ryan. You concluded with a call to develop specific tools needed to answer science questions. How do you balance specificity in our research projects with the need for general tools that might help address connected science questions?
Well, I think the fact is that you can't do one or the other. You have to do both. And whether we like it or not, to keep a vital scientific community going in any discipline, you have to provide a certain stability of employment and a certain level of funding. And that's certainly provided by the building of facilities. But at the same time, we have to understand that we're running out of money. And we just can't take last year's facility and multiply it by 2 and build the next one. So what I'm asking for here is that a little bit more emphasis on zero-based examination of the scientific priorities of what we want to understand about the sun, and then departing from those priorities to build the instruments we need to look at them.
So we have a sort of follow-up question here. Do you have other examples of focused instruments that you could discuss? Ideas for focused instruments?
Probably off the top of my head, I'd probably not want to venture that, but I think that in the few days of this meeting, I could come up with a couple of other examples and forward them on, and I'm sure that they would show up on the system in some way that organizing committee can figure out.
Oh yeah, and I think we'll have lots of opportunities for breakout sessions, and maybe one of them could be around the idea of what would be our
I'd be
this
happy
kind of
to do that.
instrument. Yeah.
I'd be happy to do that.
Thanks. And then we have another question from Ankush. It was a really nice, there was a nice slide. But instead of Dyson sphere, it could be related to the convective disturbance in the star. Do you think any specific characteristics to look into light curves can confirm this?
Well, one of the first diagnostics that was thrown at this was to measure the spectral distribution of the light curve, and the behavior of the spectral distribution was such that once again it was ambiguous because it could be caused by dust, which dims the blue wavelengths more than the red. But that's the same direction you'd expect if the sun were just cooling a little bit. Once, if you look at the Planck distribution, that would give you the same effect. So it didn't turn out to be as good a discrimination as had originally been thought, but it certainly doesn't rule out the internal storage of the energy. I should add also that a rather intriguing possibility is that this star is unique in the sense that it lies very close to the boundary between between convective and radiative transport in stars. And so if you have a star that's right at that boundary and it's flipping back and forth between convective transport and radiative, you might expect hiccups of the kind that perhaps, where the star is manifesting. So my interest in the problem was along those lines, that this star might be a really good indicator of what happens when the star is on that boundary.
We have a question here from Lika. Can you comment on the solar spectral irradiance? What do you think is the relationship between SSI and climate change and regional change, regional climate?
Yeah, well, that's a very good question. Obviously, there's been a lot of, effort put into modeling what, for instance, solar ultraviolet forcing can do to the structure of planetary waves, which change the latitudinal temperature gradient on the Earth's atmosphere. That's one example that was put forward by Joanna Haig at Imperial College. There have been many other models that extend also into particle forcing, not only UV but also particle forcing. I think that the comment I would make about the solar spectral irradiance variation is that it's a different kind of problem than the TSI, because the TSI definitely shows a correlation with global temperature, as I showed you in one of my slides. But the head scratcher, that the problem is the amplitude is wrong, where we're still looking for this factor of 3 or 4 in amplitude. That problem does not exist really with the SSI, because a model like Joanna Haig's model really doesn't need any more amplitude of ultraviolet forcing than we've already been seeing on spacecraft for decades. So one might ask, is it as urgent to monitor the ultraviolet flux as it is the TSI? Because we don't really have a problem with the amplitude that we already know exists.
Okay. We have another question just came in. Is there any relationship between solar wind speed and long-term reconstruction of TSI?
It would. I don't know the exact answer to the correlation with wind speed. The fact is that the kinds of structures that influence the TSI are sort of orthogonal to the structures that affect the wind, at least much of the wind output. Though I have to be careful there, because it depends on whether you're talking about intermittent events or long-term events or so on. But you do have to bridge the gap between the fact that the main impact on TSI is from active region magnetic structures, whereas coronal holes, which tend to occur to a great extent in quiet sun, are an important factor in determining the wind speed. So the short answer is that there probably isn't much of a correlation.
Okay. I think we have 2 minutes left, but I'd like to, and there are no more questions, so I'd like to ask a question. If we were talking about trying to predict TSI and SSI variations, what's the major roadblock there if we want to use this knowledge to help understand or predict future climate variations?
Yeah. Well, predicting TSI is basically the same as the problem of predicting the solar activity cycle. And when it's hard to believe that we're really going to have that on a solid basis until we have a proper dynamo model of how the magnetic fields in the sun are generated. On top of that, we're dealing with a phenomenon with the solar dynamos. Solar dynamos have been shown already back several decades ago to be examples of nonlinear oscillators, which are known to be chaotic under certain conditions. And so the prediction of the solar cycle, important as it may be one of these examples in nature where no matter how hard we try, we're never going to be able to predict it. You know, it's the problem that Ed Lawrence pointed out, that if you look at the equations of motions of a leaky water wheel, which is a very simple Newtonian system, you produce chaotic behavior that you can't predict no matter how much you study that water wheel.
Mm-hmm. Okay. Well, thank you very much for those answers to those questions. It's been very interesting. Phil, do you want to take over?
Yes. Thanks, Dan. Thank you so much, Peter. I've jotted down half a page worth of notes here of your ideas, and many of these are quite novel things. And I look forward to thinking about these in the future. So thank you. As a nice follow-on, we have now Professor Amitabha Bhattacharjee, and it follows from Peter's talk in directly from, I believe, from his pictures of the interacting magnetic fields that lead to electric fields that arise as a result of this process called magnetic reconnection, which is one of the biggest ways in which magnetic topology changes, etc. So, and topology in a very highly conducting plasma like the sun's corona is a major constraint on the equations of motion. So it's a pleasure to welcome Amitabha. He is a professor of astrophysical sciences and the head of the theory department at Princeton University Princeton Plasma Physics Laboratory. He also serves as co-director of the Princeton Center for Astrophysics. And today he's going to talk to us about, well, we'll find out. Welcome, Amitabha. Thank you.
Thank you, Phil, for that kind introduction. Can you see my screen?
Yes.
Yes. Thank you. The subject that I will speak about today is role of high performance computing in solving fundamental problems in heliophysics. I'm deeply gratified to have been invited to the Eddy Cross Disciplinary Workshop. The word cross-disciplinary has a nice ring to it, and I will reflect soon on what Jack Eddy thought of all this. But before that, just an outline of my talk first. As I promised you, a few words from Jack Eddy. This is a celebrated 1999 interview that I'll tell you more about in a moment. And I will make some remarks on why high-performance computing has the promise to facilitate transformational changes in science. And as an example of that, I will deal with a topic that Peter Foucault in his excellent talk just make a reference to, which is magnetic reconnection, which is an example of a computational grand challenge that truly crosses boundaries. And I'll tell you a little bit about the computing story in the DOE Office of Science. I think Peter did me a great favor by alluding to work in fusion plasma science, which the DOE Office of Science is the main custodian of, and one in which I am a participant. There is something to be learned through cross-disciplinary, cross-agency dialogue that I hope to share with you. And then from that, taking this opportunity to actually make some suggestions in all modesty for the NASA Heliophysics division that I think Jack Eddy might have approved of. So let me begin with this interview with Spencer Wirth in April 21, 1999, that Jack Eddy had. It's an excellent interview. And I have given you the citation to the website where I urge you to look at it. The American Institute of Physics keeps a number of these interviews on record, and they're truly very revealing because other than learning the history of ideas, which I take delight in, you also learn a great deal about the people themselves. And for those of you who didn't have the privilege of knowing Jack Eddy, as I didn't, I got a sense of what he was about by reading this article. And when asked about interdisciplinarity in his typical self-effacing way, he said, yes, I think that's what I was doing. And he did a bunch of quite different things intentionally. All my professional life, I have striven to be as broad as possible. My critics could rightly also say yes, and as shallow as possible. To which the interviewer responds, well, I can't fault you on that one personally. And Eddy picks up. I knew you of all people wouldn't. But my reasons for taking this less traveled road were many. One is the inevitable thrill of discovery when you wander into new areas. More importantly, you also avoid the danger of being too comfortable in too narrow a niche. I truly believe the sayings that there is no hope for the satisfied man and that without fear there is no learning. Those are marvelous words, as deep as I have ever heard been spoken or written about what it is to wander across interdisciplinary boundaries, to risk being a maverick who actually ends up being one who contributes deep insights. That will not always work out, but that is the thrill of discovery. And to all young people in this talk who are listening, may you have the license to do that. It turns out Jack Eddy did that and took substantial risks. Phil, in his nice introduction about Jack Eddy, did not tell you that his own institution, the High Altitude Observatory, fired Jack Eddy for not doing enough deep work. Fortunately for us, those days, a good woman was easy to lose, a good man less so. So he found his way into the University of Colorado math department, but he was doing no mathematics. Be that as it may, he wrote his seminal paper, and then he says later in the interview that he is one of the few people in history who was invited back to the institution he was fired from. He never went back. So Phil, you have all this legacy to live with. Being a maverick yourself, I think you'll understand. But unlike Jack Eddy, you were never fired, which tells me about the great respect in which you're held in solar physics and continue to do so. Now, I want to say a few words about facilitating transformational science through high-performance computing. A few facts. During the last decade or a little longer, the heliophysics community has gone through a radical transformation with vast increases in data rates, archival volumes, and the use of sophisticated instruments. Example, if you look at the Solar Dynamics Observatory, sends in 2 terabytes a day, which is about 100 times TRACE did and about 1,000 times than SOHO-EIT did, producing images data of unprecedented quality and complexity. If you have your SDO app, as I do, every day you can tune on and see these spectacular images. Progress in our understanding relies critically on combining data science with high-performance computer simulations and theory. And here is something that I'd like to emphasize, that in the classical way in which science proceeded, we talked about the two legs of discovery being theory and experiment. But computer simulations, which I emphasize in this talk, are the third leg of discovery. They help us explore where we cannot sense, can give us a comprehensive view of sparsely sampled environments, even with all the missions in the expanse of the universe. What we sample is very little of what the universe is about. And place the heliophysics domain into a controllable laboratory setting, all of this at a cost that is a fraction of the cost of a mission. I'd like to emphasize that because we can't always have billion-dollar missions, but if we develop our computational tools where they are truly predictive, then maybe in order to choose between different missions, we can actually have our simulation tools be predictive and tell us what we might expect to find if, by comparing these predictions with existing data, we can validate these tools. And I should point out, and this may be a bit of a pinch, is that investments in advanced computational capabilities have not been uniform in all the divisions of NASA Science Mission Directorate, and comparatively low in heliophysics. The level of commitment in earth science is the highest. And if you look at the progress that has happened in earth science from these simulations, there is something there to emulate. Now, when we say that we want to facilitate transformational science through high-performance computing, I'd like to make a few remarks, because the objective is not just to port our existing codes to bigger and faster computers. That is, if we do that, then that's an opportunity lost. Why? Well, it is not quite enough to be a little bigger and faster, because leadership computing is very expensive. And our colleagues in science, the public, and those involved in the political process will not be supportive unless we can demonstrate that our codes can produce transformational science. That's really, really important, that in order to keep the public truly engaged in our enterprise, we can't be incremental. And this applies as much to expensive missions, facilities, as they do to computational science. Example, one Blue Waters hour, and this is a computer that is being phased out, was $20,000. The machine needs to be used carefully and efficiently, like any expensive equipment. So if you're running legacy codes that are wasteful in a high-performance computing environment, you're not using these magnificent tools for what they're really good for. And therefore, an urgent imperative in the community should be to modernize our codes for high performance in new architectures using new algorithms and software. Fortunately, I will argue that we need not do from scratch, because the ecosystem already exists and can be leveraged by intra and interagency partnerships. Coming from a scientist, I know these programmatic comments might seem like not quite the right way to begin my science talk. And I won't talk programmatics until the end again. But please forgive me for making these statements, because I have made them in multiple opportunities that NASA has kindly afforded me. And I'm really, really excited about the talks that we heard earlier today, including the one from Massimo, where he made a strong connection with calculating derivatives through AI/ML. And I haven't even talked about AI/ML because I know others more knowledgeable than I will. But I did wanted to point out that high performance computing, whether it does AI/ML or running simulations, can be a powerful tool in making advances in transformational science. An example of which is magnetic reconnection. And I'm now delighted to be able to ride my favorite hobby horse, which is to tell you about how I think, as a particular example, high performance computing has truly been transformational for magnetic reconnection. In addition to the experiments that Peter, the laboratory experiments that Peter emphasized, as also plenty of astounding observations in solar and magnetospheric physics, in which we have really, really good data to constrain physical models. So I'm a theorist, and without any apology, let me just start from the beginning and tell you about the Sweet-Parker model for magnetic reconnection. As in many things in heliophysics, a lot goes back to Eugene Parker. This is taken from his paper, which actually followed Sweet's. And what he was trying to do back in the 1950s was trying to understand how to release the enormous amount of magnetic energy in solar flares and convert it to particle acceleration. And so how rapidly you could convert this magnetic energy was the question that was troubling him. And he came up with a model with Sweet. In the simplest incarnation, it's a two-dimensional model on the plane of the paper, and he's showing families of magnetic field lines indicated by arrows pointing in opposite directions across that pink intermediate region, which we will refer to as the reconnection layer. He assumed steady state. He assumed that the plasma is incompressible and that the resistivity of the plasma, assumed to be finite but small, was given by the Spitzer formula. So what he did, he went to the induction equation, well known. The first two terms, the left-hand side is the time rate of change of the magnetic field. The first term gives you the convection of the magnetic field, and the third is one of resistive diffusion. Mu0 is the permittivity. So if you do steady state, then you set the left-hand side equal to 0, and you balance this term against this term. And without even taking derivatives, he just did scaling arguments, knocked off one derivative from both sides, and wrote simply dimensionally that the flow coming in, V in, times B must be equal to balance by the right-hand side, which is eta by mu0 B by delta, which is the thickness of the current sheet. He also used mass conservation. V in times L equals V out times delta. So out of these, and using energy conservation, he came to the simple conclusion that the force with which, the velocity with which the plasma is ejected from the reconnection layer can be at most be the alphane speed. So if you want to calculate the reconnection rate, which he measured by how fast he could make this inflow velocity, you come to the conclusion that V in over VA is 1 over square root of S, where S is the Lundquist number. And this number is a dimensionless number, which is extremely large for the solar corona of the order of 10 to the power 18. So if you should rely on the Sweet-Parker model, which turned out to be an absolutely correct model, but irrelevant, because the time scale, I mean, it was of great relevance in the life of science, don't get me wrong, but the time scale it gave you was much too large than what were being observed and attributed to reconnection through solar flare onset. So this problem went in limbo for a very long time. Petschek came up with a very ingenious solution. And I'm not going to be able to go into the history of it, except to tell you that high-performance computing simulations proved Petschek wrong if one assumed that the Lundquist number was large and uniform. I don't want to take that historical detour because it would take me far too long. What I do want to tell you though, that the results of the computer simulations that were carried out in the 1970s gave a ringing endorsement to Parker's model, Sweet Parker's model, even though the timescales for solar flare were all wrong. Well, we sought relief elsewhere, but there's something we missed. That even though the Sweet Parker model was right back in the 1970s, fortified by simulations, as our simulation tools got more sophisticated, and I'm now jumping to developments in as recently as 10 years ago, 2009, where we found that through high performance simulations, one of the cardinal assumptions of the Sweet Parker theory, namely that you have a long thin current sheet and that it is stable, was turned out to be wrong. And the simulations told us that. It's embarrassing that we missed this all this time, simply because theory left us in a very interesting place. Simulations at a time did so as well, and as the Lundquist numbers got higher and higher, this is what we were finding was happening to the Sweet Parker current sheet, that it went violently unstable to plasmoids once you exceed Lundquist numbers of the order of 10,000, whereby the thin current sheet went through a rapid sequence of transformations into these plasmoids, with smaller ones merging to form larger ones, getting ejected out of the system, coalescing to forming a hierarchy of plasmoids that Shibata once referred to as a fractal regime of plasmoid reconnection. And this is what simulations made it more precise. So even a landmark in the theory of reconnection, such as the Sweet Parker model, has a flaw, that actually it is correct below 10,000 Lundquist number, and over 10,000, it is unstable to the plasmoid instability. But what does it do to the reconnection rate? So if you look at the time for reconnection as a function of the Lundquist number, things very much go consistent with Sweet Parker scaling, increasing as s to the half. The larger the Lundquist number, the smaller the resistivity, the longer it takes to reconnect. But once you have reached about 10,000, the curve flattens out. And all these different points that you see are realizations of different simulations started with different noise levels. And it turns out rather interestingly that the interesting noise level comes in as a logarithmic dependency. There's a separate theory for that into which I can't go into in this talk. Suffice it to say that if you look at the flat reconnection rate at 10,000, you get 0.01 VA independent of the Lundquist number. That's important, that even within the realm of resistive MHD, if we go to Lundquist number large enough, we depart from the Sweet Parker model, and we end up with a reconnection rate predicted by resistive MHD, which is a 100 of the alphane speed. In many kernel mass ejections and flare reconnections, reconnection rates are reported over a range from 0.001 to say 0.1. If you wanted to get to 0.1, you would have to incorporate in resistive MHD certain collisionless effects, which I'll allude to later on. And then you will end up getting, thanks to the plasmoid instability, which already takes you to 0.01, and then some further kinetic effects to the number of 0.1. So the problem of getting to fast reconnection rates independent of resistivity, I consider now to be a solved problem. And I hope that is not a statement of too much hubris, because history has found a way to make a fool out of us, or I should say nature has, time and again. And I hope I won't have to eat my words. Now, you say you see all these plasmoids. If you look at post-coronal mass ejection heliospheric current sheets, you would see blobs in them. We do not have magnetic field measurements in the corona that are direct measurements, so everything is inferred. So if you look at the blobs that you see and regard them as proxies of plasmoids, then I would say there is evidence that a heliospheric current sheet breaks up into plasmoids. And there's some really nice work done in that area that I can't get into now because, again, of a lack of time. And statistics of these plasmoids, how they are distributed, are things that our solar physicists have studied. And theorists, therefore, have challenges to meet. And they have met some of them through papers that I don't have time to go into. But in the Earth's magnetosphere, cluster spacecraft actually probe the magnetotail where current in a substorm, when in fact the current sheet is so stretched out as to be nearly Sweet Parker-like current sheets, if you will, with extended regions of magnetic field lines pointing in opposite directions and magnetic islands forming. And Li Jianchen, who's a very well-known person now in NASA Goddard Space Flight Center and done wonderful work, privileged to be her postdoctoral colleague, in 2008 published a paper using cluster data where she actually reported enormous number of islands of the kind that you see, 10 islands within 10 minutes, and she did more. She actually, through detective work, tried to identify where the energization was coming from due to particles which were going through this layer of multiple islands. And she saw energization in all channels listed on the right-hand side. And what is interesting about her findings was that whereas the so-called X points, where the islands cross an X point, which we will think are the places where the electric field is the largest, were not where the highest density of particle energization was. She actually found that the particle energization tends to peak at the middle of these islands rather than at the X point where the electric field is the largest. You got the highest energies from the X points, but the maximum number actually came from within the islands. And this, I think, anticipated some nice work in magnetic reconnection, whereby people like to solve the big numbers problem we have in solar physics. Namely, if you look at the RESI data that Bob Lynn led, in which he pointed out that half of the particles in the plasma were actually energized to very, very high energies. Now, half the number of particles is an enormously large number. If you relied only on particle acceleration at X points, you might get the energies, but not the numbers. That's what we call the numbers crisis in solar coronal particle acceleration problems. But that can be mediated somewhat if you actually have volume-filling islands where a lot of energization can occur, as Legion was pointing out, using MMS observations. I know I'm crossing huge boundaries here because I'm using a magnetospheric example to make the point about something that is going on in the corona. But magnetic reconnection is occurring in all these environments. And the plasma parameters are very different, but they have some things in common. Both are extremely high Lundquist number systems. The magnetotail, more than the sun, is a collisionless system. But even collisionless effects can be very important in the sun as well. And it therefore helps to look at this problem from a unified perspective. So now getting back to my theory slide, when I was talking to you about 2 dimensions, you can say, well, that's all in 2 dimensions. What happens in 3 dimensions? What you have in 3 dimensions is what you're seeing on the left-hand side. Looks like a Jackson Pollock type of painting, where you have a lot of these 2-dimensional objects, the plasmoids, that extend out in the 3rd direction as flux ropes, twisted flux ropes, that then grow in amplitude and become turbulent, because they started with roots in which they had some plasmoids in the first place and went 3D. If you project it in a 2D plane, you would still see blurred blobs, but their outlines are not nearly as sharp as they would be in 2D. And if you look at the energy and the magnetic energy in these regions, they're nearly at equipartition. And gradually you end up going into a fully turbulent stage, now mediated by this plasmoid instability. Okay. So let me see if I have my order a little screwed up. Okay, so I talked to you about reconnection on the small scale. Now, what I want to talk to you about is if you understand the physics, all of that I just talked about, how does it all build up to global space weather modeling in collisionless terrestrial magnetospheres? So as I made a point of stating, this is a broad interdisciplinary challenge straddling heliophysics, planetary and exoplanetary science, with implications for habitability. Are we alone in this universe? Why do I say exoplanetary science? Because one of the things that the exoplanetary astrophysicists are now doing is to use moisture as a criterion for finding life. But if we learn from our experience in space weather in the heliosphere, we will soon come to the conclusion that life we may have on the Earth, as we do, but it can be endangered by a serious space storm like the Carrington event. Now, if you go to some of these exoplanetary systems where the exoplanets are very, very close to the sun, you do not need an event of the Carrington variety to blow out the atmosphere out of the exoplanets. And one of my colleagues, a Jack Eddy fellow, Chuan-Fei Dong, has actually used global heliospheric codes to model, say, TRAPPIST, which is a well-known exoplanet and a well-studied one, and has come to the conclusion that if TRAPPIST had a space storm, which is a fraction of the strength of Carrington, that would be enough to blow out the atmosphere in TRAPPIST, even if it had moisture. So we want to prepare ourselves for developing our space weather tools, not only to teach about space weather in the heliophysics or in our planetary system, but also in places where we are looking for life. And traditional global models based on MHD have largely run their course. Reconnection, turbulence, dissipation, and energetics, especially the kind of things that goes on in narrow layers, is not accurately modeled. If you put in anomalous resistivity and viscosity, you're fudging it, because by fudging them by hand, you can actually do just about anything you can. That's sad but true. And given the sparsity of observations, you can always get agreement. You therefore have to be careful and go into the fundamental physics of what is going on in these narrow layers. And for that, you need to go beyond MHD. MHD itself is taking you to very thin current sheets. It's taking you to reconnection where things don't depend on resistivity anymore. And if the thickness of the current sheets would become comparable to the ion skin depth or the ion Larmor radius, you need collisionless physics. And unless you put that physics in, you won't be truly predictive. So the science involves intricate interplay between small and large scales. Small scale dynamics have major global implications. Global dynamics drive local processes. It is not possible to do one without the other. And this is the grand challenge that you have, which is why you need high performance computing. You have a kinetic scale, you have macroscopic scale. The kinetic scale goes from electrons to ions, MI to the ME to the half separates them. And you have orders of magnitude separation between the electron ion scale and the macroscopic scale. So is it true of the time scales? The Alfvén time scale that I talked about, which is way, way larger than the cyclotron scales on which heating often happens. And you will not find one simulation that will bridge the divide, not even in the present reach of exascale computers. Fluid simulations cover this range at the present. Kinetic simulations do the green arrow. The grand challenge lies here. And so it will take an extension of fluid simulations which incorporate kinetic effects as the next frontier in solving the reconnection grand challenge problem. So what are we doing now? And I'll focus on the magnetosphere for the moment because that's an area I know a little bit about. And what you're looking at is what can we do today? Well, fluid codes can do magnetospheres, but we can actually do a little bit better with hybrid codes. This is a code that was built by Homa Karimabadi in UCSD and now in a separate company thereafter, and now it is in Los Alamos, which has gone further modernization. And if you put in a PIC box, a kinetic box, you can typically do on supercomputers, something on the realm of 1RE. So kinetic theory is wonderful, but it really can do only that VPIC box, that little box. And that is now at a mass ratio of 100 to 400 to give you the magnitude of the challenge. But what you really need in order for global space weather modeling is to incorporate kinetic effects and fluid codes. Thanks to the strategic partnership between NASA and NSF, that Madhulika had a big role in leading and allowing us the privilege of actually building exciting new codes, we actually built a computational framework for global simulation of collisionless plasmas with the following attribute, that we were able to study processes occurring at ion and electron scales with scale separation between ions and electrons, but we could not do realistic mass ratio even in the fluid limit. We went up to something like 1/250 to include new equations of state for electrons and ions with physics-based closure. We could handle multiple ion species such as hydrogen and oxygen, thus enabling the coupled treatment of composition, wave, and instability dynamics in the magnetosphere with its implications for space weather events. We used high-performance computing techniques to the limit by using state-of-the-art algorithms, scaling them up to thousands of processors on modern computational architectures, many of them owned by DOE. And we have done some validation and verification, comparing with data from Ganymede, from Mercury, and from the MMS mission on Earth. And last but not the least, our codes are completely open source and accessible to community through GitHub. And you also have versions of them available to the CCMC at NSF. So here is a Mercury simulation done by Chuanfei Dong and others. Again, as I emphasized, this was a Jack Eddy Fellow who now has a staff position at the Princeton Plasma Physics Laboratory, I'm pleased to tell you. So we managed to stabilize his career. And what you're seeing here is Mercury being simulated for a storm. Mercury has a rather remarkable feature in that its core couples to the magnetosphere. And we were able to extend Jekyll by actually putting in a core in it, high sigma core, high conductivity core, low resistivity with a mantle which is low sigma, that is then matched onto the global magnetosphere. And here is our effort at trying to reproduce the magnetogram data from a messenger that Jack Slavin and other people provided us. And as you can see, we have successes and we have failures too. The failure in the very rapid spikes, for which we need to put in more physics, more kinetic physics, we believe, that is highly impulsive. And this is work that is going on, and this was featured as a cover in GRL. What I want to share with you is something that is going on in another agency. As what is going on in the life of science in particular, and I feel a little bit licensed to do this thanks to Peter, who actually referred to a tokamak diagnostic. So you'll be pleased to know, of course, that the DOE Office of Science has picked up on NASA's historic lead in high-performance computing. NASA was a leader in this and frankly dropped the ball when it shouldn't have. That's no criticism. Pressures on agencies make them make choices, hard choices sometimes, but they were the ones who led the revolution at one point. It was taken up by the DOE Office of Science, and they brought a 20-year commitment that has brought it from the teraflop era to the petaflop era, and now moving on to the exaflop era. For those of you who are keeping up with the computer buzz, Argonne National Laboratory and Oak Ridge National Laboratory will have the first exascale computers this year. Frontier in Oak Ridge and Aurora in Argonne. The story began, though, with multiple centers in the Scientific Discovery through Advanced Computing program, which brought together domain scientists, applied mathematicians, and computer scientists. The latter have developed mathematical algorithms and computer software that maximize efficiency on high-end computers. This prepared the ground for the exascale computing program, of which I'm part, which is now the highest funded program in the Office of Science, surpassing ITER. So I want to just tell you what the exascale computing project is now doing. Application development, software technology, exascale systems, hardware technology. This is a multi-billion-dollar program right now in the DOE Office of Science. And they have 23 projects. The one in red that you see is the one that I lead as principal investigator. Is whole device model of magnetically confined fusion plasma. And what this tries to do is to really solve a problem that needed to be solved in fusion physics. It turns out that when you look at fusion plasmas and what controls energy confinement in these systems, you would not be surprised to learn that it is primarily turbulence, because we have tamed classical transport by good design. And so essentially the problem of fusion boils down to how well we understand and can be predicted about turbulence. Now it turns out that the turbulence in the core of a fusion plasma, and you can see this visually in the left-hand side. This one, the left-hand side code called gene, has a big gap in the edge. The methodology used to track the core turbulence, which is slow in time with different types of spatial structures, is very different from the edge where the turbulence is much more rapid. And the methodologies that have to be used, both kinetic, take different forms in the core and the edge. These have never been coupled together in one simulation. And the goal of the whole device model that I have the privilege to lead, which is a multi-institutional consortium, including plasma physicists, fluid dynamicists, applied math, and computational science experts, is to make this kernel happen so that we can make it for a whole device prediction. And this is what we have done. And I don't have the time to go into this except to say that this is the kind of thing that I think would be good to do for NASA heliophysics as well. And I therefore would like to dare make—
5 minutes, Amitabha.
Yep, and I'm near the end. I would like to dare make some
Thank you.
suggestions for that. Thank you, Phil. For NASA heliophysics division that Jack Eddy might approve of. And I think of him as a person who tried to look at the big picture, tried to learn from people who knew some things better than he did so that he could teach them too something that he knew better. And by taking risks and by talking to people across boundaries, he was able to put both communities forward. So I've discussed here the influence of high performance computing on transformational science in heliophysics, but through one challenge, reconnection. I could give you similar talks on solar wind turbulence and on the dynamo problem that Peter referred to. These are wonderful subjects ripe for cross-disciplinary work. My suggestions are build and support teams led by domain scientists who will collaborate with applied mathematicians and computer scientists to develop high-performance computing tools that will exploit the power of modern computing facilities. Build on strong partnerships between NASA and NSF. You already do that. And begin new ones with DOE as recommended by the DRIVE initiative in the Decadal Survey. The DOE Exascale Computing Project provides a good entry point that the ECP seems very receptive to. And you have invited people from the ECP to come and speak at your multiple workshops. The important point is to live in the same ecosystem of computing and run simulation codes on state-of-the-art computer hardware that can enable transformational science. Organize data science and computing in NASA SMD in a way that will integrate software and hardware management, spanning all SMD divisions. Empower your hardware people to become true partners, and in partnership with each division, setting its science priorities. Encourage domain scientists to compete in programs such as DOE Insight ALCC, which provides access to enormous amount of software. The Exascale Computing Project has 78 software technologies that many heliophysicists will find attractive. Have a high bar for code performance. Your database demands it. SDO is so gorgeous in its predictable power. I cannot imagine too many lab people have data as beautiful as that, or as highly resolved data as you have from the NASA MMS mission. Make your codes try to compete to really have high fidelity predictions for such a wonderful database. George Sisco taught us many things. And one of the things he did teach us was that do not wait for the perfect simulation code, which is impossible without continuous validation and continuous guidance from data. Prediction imperative should guide physics imperative, not the other way around. And I think the meteorologists have taught us that this is the case. And I would have liked to also say before I end it, Gene Parker was a theorist, and he always did pen and pencil work. In one of his birthday festivals at which I was invited to speak, I like to quote from him when he said, remember, when you do all this work, this is terrific. Computers are great, but don't forget fundamental physical principles of the kind that you can do on pen and paper. So if you can't make sense of your simulations, sometimes through heuristic estimates, chances are your simulations are misguiding you. Be careful about that trap too. We have a lot of things to think about here. Let me end on that note. Jack Eddy was a person I think who liked us to take courage and uncertainty. Thank you for your attention.
Thank you so much, Amitabha. As usual, a really thought-provoking presentation. I'm struck by your statement of the third leg of science advancement. I think we saw the first two very clearly with Peter this morning. And I personally am very convinced of the power of computation in enabling us to look at numerical experiments and understand the science. So your talk is really an excellent example of that. I'm going to hand over to Dan. I think he has some questions for you, but first I will just say thank you so much again.
Thank you. So yeah, we have a number of questions in the Slido chat, and again, those watching, please feel free to add questions and also vote on the priority of the questions that we may run out of time here. So the first question is, thanks for the important perspective. What skills are missing or lacking in our community with respect to computation? What capabilities do we need to cultivate?
As I said, enormously good work has happened in the community already. And look, the codes in your community are doing extremely well in keeping up with the stream of wonderful data. The first thing I'd like to say is getting all this wonderful data is not enough. I always feel like we are not mining what we have in our hands and get good physics out of it. So the first thing I would like to say is please prioritize learning from what you have, strengthen theory and simulation. I know coming from a theorist, that seems like a plea for money, but this is not what I really mean. What I really mean, in order for us to have really imprint, go beyond the catchy articles in Nature and Science and get all that we can truly from all that we observe, that's the first priority. Second, computers are getting very powerful and very expensive, but let's make use of them. And if we make use of them, that means that we'll have to change our codes in order to take advantage of new architectures. This might mean that the algorithms that we have used in the past need to be thought through again. Fortunately, you're not on this journey alone, because the ecosystem of computing exists already. Our world is quite interdisciplinary. The agencies have to find a way of talking to each other more and sharing resources. And what I see is that we are at that particular cusp in history where I see enormous willingness, if only the bureaucratic red tape can be cut through by the program managers themselves without waiting for the highest ups in the government to speak to each other, they can do a tremendous amount of good by reaching out to their colleagues. And then once you do that, one of the things you can do that is to encourage more code development as part of your science pursuits. For a long time, NASA actually did not allow code development. So people tended to use the same codes, legacy or not, to make sense of more and more sophisticated observations. But your needs are specific. Allow people to develop this. And I must say, Madhulika, when she co-partnered with NSF on the last round of strategic partnership, gave us that freedom, which is why Jekyll came about. That's a good example to follow. We need more of it. And we need young people, early career people, first and foremost, who are not sold on old ways of doing things, will come in and teach us new computing things to do. This is your world to conquer.
Thank you. So the next question we have is, with exascale computing, there is the challenge of storing massive data for offline analysis. What are your thoughts on how to tackle this? And I'd like to add to this that this is not just a heliophysics problem. This goes with climate modeling, and there are lots of discussions now about how storage costs are just it's not practical with the way we're going forward. So I'm curious to hear your thoughts on how to tackle this big problem.
You and everyone else are actually asking this question, and as Dan just said, it's everyone's problem. I think so far we have just about managed, just about is the word. And I don't know, to be honest with you, I think that hardware also has to get more sophisticated in order to have greater storage capacity. Fortunately, storage doesn't cost as much as computing. So that is something that people are still able to do at the high performance computing centers now. And so what they do is that you run this at the computing centers themselves. And as you know, DOE has invested heavily, as has NSF, in cyber computing, where they have major storage sites. Not all the data is necessarily transferred over, but selectively, depends on the users. And I think that we need to investigate in NASA similar models. And we need to empower our high performance computing people in NASA more, where they are not merely the custodians of the clusters that they manage or lead and so on and so forth, but also to have a staff locally who are experts in this, who can work with the users away in much the same way as these high performance computing centers work. Those have to be specific to NASA SMD mission.
Thank you. Yeah, I'd like to add that I think that this paradigm of generating masses of data that are post-processed later is probably on the way out, that in situ visualization and analysis is, without relying on having to dump everything to disk, is probably the one way to get around
right.
it.
I should have mentioned that. And what I should have said is what I mentioned, that in the framework, we need certain workflows and in-memory setups, particularly with the modern architectures, which allow the users access to rapid visualization packages and determining, as you just said, Dan, what you keep and what you don't. The file reading, which we used to rely on a lot in post-processing, has now become a thing of the past. In our project, we do everything in memory now. Thank you for making that point. I failed to do that.
So I have another question here about machine learning and AI. It says, when working with undergraduate students recently, I made a distinction between AI and ML and simulations. Perhaps I overstated this case. Is there a potential for crossover or hybrid work that joins the two?
Oh, absolutely. And you know what I was delighted about? I was delighted about the fact that our first speaker actually showed you how you could take AI/ML data to calculate derivatives. carrying that program forward. And for example, one of his co-workers listed 4 names was actually Brenner, who is a biophysicist and fluid dynamicist at Harvard University. And what he has done is to actually use data to construct theoretical equations for complex simulations. And it's also been done successfully for plasma simulations. That is that suppose if you didn't know Newton's laws in plasma physics, which is the Vlasov equation, would you construct it from the data numerical simulations? Guess what? That effort has been tried and it has been successful. So let me now come to our own models and limitations and how AI/ML might improve it. Take this problem that I discussed in some depth, which is that you want to bring in kinetic effects into fluid codes because we can't pick to global magnetospheres or to the corona. So how do you extend our equations? So you have this problem, how do I get kinetic effects in? So you make models. But the models, even though the good ones, have failures, okay? But suppose if you test those models against particle and cell simulations, which are fully computing on a smaller scale, and then lead AI/ML to suggest how you can improve your model, there you are. You're using high fidelity simulation data to improve your fluid model by comparing the output of a fluid model with a particle length simulation and then using the fluid model for making global prediction. It is a tremendous AI/ML tool that we are not making use of. We are focusing right now a great deal on AI/ML techniques to make sense of data, which is, we should, that's great. But we should also do on how we can improve theory, because theory could also benefit from these studies.
Yeah, and I think there are parallels there with just the problem of clouds and climate models. And we you know, the cost of cloud resolving models is just needs to be overcome somehow.
Rajesh just made an interesting comment in the chat, and he said that non-parametric models are advancing this area. I refer you to Rose Yu at UCSD. So I hope you heard, either saw his message or you heard me speak it. Very interesting work going on. I'm well aware in other areas of physics, and this is what we need to do.
So a question here, what triggers the reconnection in Sun and Earth and how are they different?
Excuse me, could you repeat that question?
What triggers a reconnection in the Sun and Earth and how are they different?
This is very, very nice question. One of my favorite topics. I'll tell you something. Onset of rapid reconnection is still not a solved problem. What I did say was a solved problem was once you have onset, you can get fast reconnection rates and what physics you need to get the fast reconnection rate. But how do you go from a state when you're very quiet to one that you have sudden activity, a change in the derivative of the curve? In the solar corona or in the Earth, we thought for the longest time, and this is what the plasmide instability changed, that what you need to do is to first have Sweet-Parker reconnection, which is rather slow, then wait for that reconnection layer to gradually shrink in size until it falls below kinetic scales. When Hall MHT and other kinetic effects become important, giving you a sudden enhancement in the reconnection rate. I was part of that understanding, and I felt in my life I at least helped solve one problem definitively. And then 10 years later, I changed my mind. What did we find? We found, in fact, that the Sweet-Parker layer itself is unstable, and it can be violently unstable to the plasmide instability at a sufficiently high Lundquist number without having a slow phase. So now the problem is that every time you get a thin current sheet, you get the plasmide instability. How do you get a storage phase where you store a lot of energy? The reconnection must be sufficiently low, but the plasmide instability screws you up. So now I have to ask again the opposite question. How do I get a slow phase and then transition? Problem that is not yet solved. I'm hoping some really smart student on this talk will solve the problem someday.
Okay. We have maybe a chance for 1 or 2 more questions if we're quick. Thank you for emphasizing.
Very quick, I apologize. My answers are longer than they should be.
That's all good.
Okay.
Yeah, so I think, thank you for emphasizing open source code. Can you describe the importance of openness in our science and what is required to make our research progress more usable?
I think open source is very important. You should take a code and break it so that it can be better. 2, open source always gives you more collaborators to improve your source code. And if you are not a control freak, you'll get and not too worried about being wrong, you'll get a better code back. I'm all for open source.
Right. All right. That's a how best to reduce the carbon footprint, excuse me, of HPC usage for heliophysics simulations? Are GPUs the way forward?
Certainly for particle and cell, GPUs have already proven to be a way forward. The exascale gives us almost 50 multiplication factor of performance for particle and cell codes. Fluid codes, particularly those using implicit algorithms, are much harder to parallelize. We need a breakthrough in that area. For explicit codes, they are actually performing really well. Astrophysics codes more than heliophysics codes at the present time, but I think they should be GPU enabled.
Okay, great. I think I see Phil again, so I think our time is up. Thank you very much for interesting discussion and presentation.
Thank you both. Thank you all for your questions.
Thank you, Dan, and thank you so much, Amitabha. Now, I'm just going to take a moment before I introduce the next speaker to remind everyone that while we have a kind of monolithic block of talks this morning, the afternoon is going to look rather different. And at 1 p.m. Time in Colorado, I believe we moved to the lightning poster session. So this is the opportunity for us to learn from the poster contributors, many of the young people. And I want everyone to be reminded that, you know, this is the source of novel ideas is all in the young people pretty much. So please do attend that. And it's my pleasure now to introduce, we move back to where we started today with computational science. And we're very lucky to have Professor Rajesh Gupta, who is the founding director of the Heliophysics Data Science Institute and a distinguished professor of computational science and engineering at UC San Diego. He is going to talk to us today about the emerging discipline of data science. So welcome, Rajesh, and I look forward to hearing what you have to share today.
Thank you, Philip. After the amazing talks by Peter Foucault and Amitabha Bhattacharjee, the real scientist, I feel like an imposter here. I'm only a computer scientist, but it is the occupational hazard that I must face because the transformation that is coming in academia, especially with the rise of data science, is no less significant than the rise of engineering from a polytechnic legacy nearly 200 years ago. And as grand as that sounds, it is filled with many potholes and experience in humility. So with that, I want to actually go back a bit, maybe not 200 years, and show you a picture. This gentleman is Milutin Milankovic. Milutin was a Serbian civil engineer trained in Vienna. He built bridges. He had a patent on concrete structures, reinforced the concrete ceilings. He was married, newly married in June 1914, and was on a honeymoon in the Austro-Hungarian Empire in July 1914. Now, July 1914, being a Serbian in Austria, was not a good thing. And he was arrested those of you who have a bit of a interest in history. And he was sent to Budapest under house arrest with the provision that he could go to the library of Hungarian Academy of Sciences. And now here is an engineer, a structural engineer or mechanical engineer with time on his hands. And so what he does is, at that time, there was a debate raising in Europe about the age of Earth. And the estimates ranged from 6,000 years rooted in literature, religious literature, to a few million years. Geologists like Louis Agassiz had found evidence of glaciers in warm southern French steppes and later everywhere else. James Kroll, who was actually started as a janitor in Scotland, in 1860 put forward a theory of climate change in a philosophical quarterly magazine that was caused by changes in the shape of Earth's orbit. This theory at that time, of course, didn't have much traction because the calculation showed that the last ice age was much older, about 80,000 years ago. But that evidence got Milutin Milankovitch, with no training in meteorology or geology or astrophysics, to study this. And he studied works by astronomers like John Herschel, of course, Louis Agassiz, and so on. And what did he think of that in his isolation? Let me see if there is a chat here. I hope it's not for me. Philip, please do feel free to interrupt me. My setup doesn't really allow me to see the chats that much. So, so he studied them, and what did he think of that? He thought that, and this is his words, most of meteorology is nothing but a collection of innumerable empirical findings, mainly numerical data, with traces of physics used to explain some of them. Advanced mathematics had no role in that science. And he took a period of 4 years to make sense of the planetary motions, calculating the amount of solar radiation at different latitudes for over a period of 650,000 years. And he published that into a book called Contributions to Mathematical Theory of Climate, that turned these hundreds of pages of handwritten astronomical and climate observations into a relatively simple model. I'm going to make it even simpler, and most of this audience, I'm pretty sure, knows a lot more than I do in this area. That there are basically 3 variations in the that affect climate: eccentricity changes, obliquity changes, and of course we know about precession. Sometimes precession correction is often known as a Milankovitch correction in GPS. And the years passed. Of course, Milankovitch went back to his profession, and the scientific community ignored him up until some evidence started appearing. In the meantime, he moved on to writing science fiction about future and so on. And this is a paper that comes from 2016 in Science, and basically looking at the oxygen isotopes in the shells of seabed deposits. The stages of glaciations can be actually sort of computed almost like the way you do EKG from various different timing signals that overlap together. And so it turns out that he was onto something simply by taking the observational phenomena, but the observational phenomena itself wasn't enough. In fact, what really was extraordinarily effective was the unreasonable effectiveness of mathematics in explaining our natural world, whether it is physical world or chemistry or almost all the natural sciences up until today. Mathematics is that universal solvent. Now it turns out we are heading to this, and some of these talks today are referring to that, is that our data is becoming a way of, is the universal solvent that is beginning to give us insights into many, many domains. Not the same way, not the same mathematics that we have been used to from Newtonian onwards to the one that we have in new mathematics emerging, very early stages of that. And we are only beginning to see this. Those of you who have ever tried Google Translate or image recognition, pick up any image and look at the content of that, and chances are very, very high, whether it's Google or Facebook or something, that quite a bit of recognition has been done. In fact, one can make the case that if there exists a pattern, maybe some of those patterns which might be non-intuitive or difficult to spot by human eye or mind, can be spotted by the new class of algorithms. So what I want to do today is lay out what is data science, or at least this new field that is emerging. And again, the mindset that I'm going to bring you is exactly the same mindset that Napoleon had when he told Sadi Carnot about building the science for converting heat to work, or materials for metallurgy for making steel. So I'm going to share that to you, and in particular, I'm going to focus on the notion of platforms, because I think that is something that you might walk away with as a framework to think about what the new advances are bringing to. And then I'm going to share with you with a bit of a chutzpah about how we see data science emerging in San Diego, and what are we doing in actually building this discipline. And this is not just a scientific challenge or a mathematical challenge, but it's also an organizational challenge. Our universities are a lot older than engineering, and but even then, engineering has led to transformation of university, and I think we are now due for a new transformation of how we think of academic areas and how they're organized. And I think some of you have hinted to that, including going back to Jack Eddy's penchant for being interdisciplinary. I think we are going way beyond interdisciplinary to a new domain of transdisciplinary education and training both. And then hopefully, time permitting, I will lay out some of the epistemological challenges of this discipline, which is a bit more into philosophy, but it still is important to understand before we sort of can answer the question as to what data science would look like, what the organization would look like, and what the talent would be. So data has always been with us. So what has actually changed? And the way to think about what has changed is to start with what we are familiar with. If you look at the IT infrastructure, information infrastructure today, that makes the access to this data and makes transformation of this data, visualization of this data possible, you would agree with me that a distributed cloud is a big part of it. In fact, it is the means by which this symposium is happening today. It is the means by which we are able to pull together diverse services, whether they are in collaborative space or whether they are in business and finance through altcoins. So this platform is supported by another platform that is at the edge of the devices. In fact, no matter what screen you're observing this talk on, is at the edge of that network. It's not only the edge of the electrons ending on the phosphorus screen or LED screen, but it's also the end point of a very deep stack of intelligence and processing. But in between the two, there is a whole new tier emerging, what we call internet, and that tier itself is due for segmentation in terms of how various design choices can be taken that serve very different needs, whether they are exascale computing needs to cyber physical systems such as transportation systems or smart building needs. And so this here is most familiar to us by a device that fortunately or unfortunately almost all of us have in our pockets, and that is the endpoint device of smartphones. Now it turns out that it's no longer really the endpoint. It is actually a gateway. It is the aggregator of a lot more sensing information, including human sensing information. And what this platform allows you to do is to create tools that go from perception to action. And I want to give you examples of perception to action as to what they mean, so that you can start to pull together in your mind the gamut from endpoint devices all the way to cloud computing, and how do they all come together, especially if you are looking at it from the point of view of platform capabilities that will migrate from one set of instantiation of a stack to the other. So what I'm going to do is show you some of these perception, cognition, action loops that are already in progress. And they're maturing very fast. I mean, they're maturing fast at the scale of months and years, or even less. So one action loop that some of you might have already experienced is the car, and it's getting much more autonomous. If you ever had trouble with parallel parking, probably that trouble is going away. It doesn't matter which car you drive. And so if you look at the vehicles, whether fully autonomous, level 1 to level 3 or level 4 or level 5, doesn't really matter. You have perception that is happening, whether it's through the cameras or through the radars, and that perception leads to a cognition of understanding scenes, and then of course the actions on the car itself. Similarly, you have autonomous drones, which look at scenes from a different vantage point, and also have an understanding of the environment and airflows, and based on that, they can, for example, confine a fire cloud or a toxic cloud, for example, simply because they're not only seeing what is on the ground, but also sensing what is in the environment. Similarly, you have smart building. This is an area that is very close to my heart and work, where you can think of buildings as nothing but another platform upon which your programs can be running, just like the programs are running on a car or on a drone. Now, in all of those cases, generally you think of a car being programmed as a programming of a computer inside a car or a computer inside a drone. But over time, you will see that the computer will actually meld into the background. In fact, in case of buildings, it is already beginning to do that. You think of the HVAC handlers. You can think about variable air control valves. You think about temperature sensors as resources one would have in a computer as memory or storage or I/O. So it's not a smart building is not a computer inside a building, but a building itself whose resources are discoverable through new means of data and sensing and methods. Similarly, you have power grid, electrical power grid, that is also becoming distributed and responsive. In fact, probably rapidly so, simply because just embedding computers into a power grid is almost is a certain invitation to all the malware and the attacks that it is subject to because of the vulnerability. So these labs are important, but one lesson that we are learning across all these platforms, whether we do it real time or whether we do it offline, is that because of the nature of the internet, and some of these platforms, by the way, do not need to use internet, and in fact there are parallel alternate architectures that can still keep it going. They allow us to scale the learning significantly. Just to give you an example of an autonomous car, the data set that, let's say, Tesla maintains about all cars, which are always connected on the internet, all the path that they take when they avoid an obstacle can actually be summarized. In fact, it is summarized so that a when I am driving my car on the same route, it is benefiting by the experience of hundreds of thousands of cars that have already taken that route in the past at different times. So that learning, that experience from a large scale scaling of data collection and summarization has many benefits. We are already seeing that, for example, in language translation, in grammar corrections, in speech recognition, and so on. So these platforms are also changing the way we think about computing itself and the computer stack. For example, when we think about a computer, at the end of it, at the core philosophical level, all it does is there's an address and there's a data, and the data has an address. You reach at that address. Sometimes that data means something which is a frame on it. But then when you start to organize data in key value stores, which are extraordinarily efficient, you can actually take the information which we call data about data. For example, a sensor data, where is that sensor located? What is it doing? What is the environment in which it is located? And the so-called data about data or metadata itself becomes a valuable part of the computational stack, just like address and data dichotomy was. So discovering and using resources, for example, when you write a program, the way you address the memory today is very standard. What that address will translate into, what methods will be using it for direct memory transfers or caching and so on, are somewhat of a standard across the entire computing milieu. But when it comes to, for example, addressing a sensor, let's say HVAC airflow sensor that is installed in one particular building, the metadata with that sensor is very dependent upon what the building is, who the vendor is, and how it is named. Now, but there are now methods emerging that allow you to use that metadata to discover these resources. And then, of course, you have the whole high-level capabilities of virtualization, attestation, security, that sort of government policies, which might also be dynamic. So the sum total of all that, and this is a part of a research center that I'm part of, led by my colleagues, Prabal Datta and Anthony Rowe, out of CMU, is called Conic Center, is advancing a number of technologies that sort of are defining new sets of capabilities. And I have to tell you that these capabilities are at the very early stages of formulation. We have, of course, heard about machine learning and models and methods. I will have a chance to just summarize you in a couple of slides how I see that. But then there is also a new programming stack, which is very different from, for example, programming on your Microsoft Developer Network or a new stack. There is also awareness of location and time. There is coordination and data transformation while it is in migration in flight. And then, of course, there is cognition and endpoint accelerators. Those of you who have heard the terms like TPUs and NPUs, in addition to GPUs, these are accelerators either built out of ASICs, custom chips, or out of field programmable chips, which are customized for a particular application. And those are now means by which we make the cost of computation stack much less. 2 to 3 orders of magnitude reduction is very possible. So to the point that Amitabh was making, that this community needs to get smarter about using GPUs and new codes in order to make use of this exascale computing. I think you need to go even one step further, and there are now programming tools and methods that allow you to use custom accelerators and therefore actually benefit from the advantage that that your partners in crypto space are already doing that in their mining and so on. So there is ways in which the data can be used that we had not even imagined previously. For example, of course, we know about social media data and how it has already changed our democracy. I won't say for the better, not yet, but though there is still the promise. There is probably more misinformation than there is information. But out of this chaos will arise new insights, new levels of training to cut through it. But then there is my colleague Rob Knight and Larry Smar looking at a map of gut microbiome. As some of you might know, gut microbiome data is about 100 times more genetic information for each individual than we have in our own cells. And they affect everything. Everything from our physical health to our mental health to right now, for example, COVID. The first reaction by body is actually in the lower intestine, not in the lungs, because that's where the ACE receptors are. And we see the evidence of SARS-CoV virus, for example, in wastewater much sooner we see it in any other emissions. Climate change is a big part of such data analysis. And now we have methods that are emerging that sort of do a pretty effective imputation of data, since data cannot be collected in all places, all times. There's genetic information, there is urban planning information, and so on. So you are beginning to see new methods and algorithms that are inspired by biology and new algorithms that are coming just by looking at, for example, fruit flies and their behaviors, or new chemistry. For example, toxicology doesn't require you to kill a large number of animals by titrating each part of each molecule for amount of toxicity. In fact, you could even estimate toxicity based on the data you have through what would call intelligent interpolations, and therefore you can sort of take a molecular structure and determine the toxic effects. Similarly, machine level predictions can be used, for example, in informing judges and crime prediction. Now, as we go from physical sciences to social sciences, the level of uncertainty increases, the level of noise and misinformation increases, and the level of hype increases, and the level of real value decreases. That doesn't mean it is not valuable, but it is going to take time. So any of these are affected by advances in machine learning. Now, what is machine learning? And of course, this is not a tutorial about machine learning, but I'm just going to take a sample point because it has had the most impact and led to a Turing Award for 3 of its original inventors. When we think about, for example, non-parametric models, these are the models where you'd have no idea what these parameters actually stand for, as they would, for example, in a Newton's law or in a relativistic calculus, because they are not derived from those first principles. That doesn't mean their math is not coming up. In fact, quite a bit of work is going on in the mathematical modeling of how neural networks work. But there are 3 large-scale developments that have made it possible for them to achieve real breakthroughs, and they're all go under the title of deep learning. And they're called deep learning simply because the depth or the number of layers of networks has risen significantly, and the reason for that is because there's a large amount of parallel computing that has been made possible at low cost, at low power, certainly, and that has allowed us to build really deep neural networks that are able to identify quote-unquote features from the data sets at multiple levels. In fact, now we have new architectures that are informing and guiding these feature sets with additional inputs or feedback loops. Also, because of internet, there is a large set of training data. All those cat videos going up to the YouTube actually had a big impact because we knew what that video was about. And because of that labeling, it allowed us to train these networks much more than anyone could have done in any lab or any offline data. So there were breakthroughs, and I just took some of them from 2008 to 2015, handwriting recognitions to speech recognitions to drug binding sites. We pick up any of these. If you were to do it from first principles, as we understand in the scientific tradition of last 200 to 300 years, they will be immensely complicated problems, whether they are speech recognitions, whether they are object recognitions, and so on. But But in these non-parametric models, these are networks that are able to discriminate first very well with very decent distribution of probabilities, whether you're looking at a picture of a human or a picture of a cat or a dog or whatever. So these discriminative networks need a lot of training data, which is why it's often known as supervised learning. But in last 5 years or so, unsupervised learning has taken on a real acceleration. And here, the unsupervised learning, really, the training is done by another network, which actually generates the inputs. You can think of a video game, for example, generating inputs. You can think of a simulation generating input. And these are generative networks. Now, generative networks can be in an adversarial game in which they try to foil and therefore improve the quality of discrimination. So when you put them in a feedback loop, the so-called generative adversarial networks and their many incarnations are now accelerating the discovery pretty fast. In fact, if you have ever seen a fake video or a fake picture or a reconstruction, let's say colored reconstruction of a movie which was black and white, chances are very high it is coming out of a generative adversarial network. And therefore, these things are making a big impact. I'm going to now give you a few vignettes of attempts that are going on, successful and unsuccessful both. And I will probably skip a few slides just in the interest of time, just to flash you the examples. But I think you can extrapolate to your domain very well from there. Before I come to the more substantive questions about what data science is. So, for example, healthcare is almost always about when you go for a treatment, about taking symptoms in and mapping those symptoms to what you might have experienced or what is documented before you do a diagnosis. And of course, there have been efforts by NIH by trying to combine the exposure or the environmental influencers and the genetic influencers to kind of create a unified picture. That has now come into a new regime of what we call All of Us, where these data gets integrated. And they basically ask a very fundamental question. Can we detect patterns from symptoms? And the answer is, of course, that's what the doctor does. But can you do it automatically, or can you do it in a bit more reliably? And so, what is the data set? Well, there are lots of notes. Thankfully, with at least the computer entry, as painful as that is, we are not subjected to the handwriting of doctors or physicians. But other than that, you have orders given, labs results, diagnostic codes, time series data, where actually majority of the sleuthing happens not from the data itself, but something that might look outlier. It might be outlier because the data itself was wrong, or it might be outlier because it was not taken correctly, or it might be outlier because there is something going on underneath. The challenge is there is no supervised learning here. You have input data, but what is the output? Maybe you have some genomic data that you can look at expressions of some genes which might be connected to some other phenomena, but these are highly non-linear. The entire body is in a homeostatic balance. It's not input-output system, and therefore it is not explainable. Linear models are very explainable, but when you come to more complex models, you might be following the error too closely. And in fact, this is a popular cartoon that I'll just leave you for a few seconds. But basically, you have a whole class of machine learning models, and there is a cottage industry that is emerging that tries to match a given data set from a given domain to the right model, whether it is, and which is much more predictive. And in fact, one of the projects that I'm involved in is looking to build a sort of a Google service for you give me a data, you give me a model, I give you a matching a score, just like we do a discriminative networks. But it's a hard problem. Can we do some crowdsourcing, like patients like us or expert networks? Again, the variability comes us. comes and bites us significantly. Many of you are in healthcare, in physical sciences, so for you, this level of uncertainty will probably make you very queasy, but this is the level of uncertainty of knowledge in health sciences that a doctor has to actually practice and confidently give you confidence in the treatment when there is actually not really a lot of underlying information available. There was a thesis, and there still is a thesis in progress, that maybe you can build active feedback loops with physician experts and patient participations that sort of will give you a better predictive ability. And there is a whole industry of how this data is pulled together, how is it integrated, and so on. In fact, IBM Watson had pulled that vision together, and it's not the only one. But quite honestly, after, I don't know, 5-6 years, there is no evidence that this actually works today. That doesn't mean it will not work. What it tells you is that we are at such an early stage of knowledge. It is almost this, it's almost like Priestley discovering oxygen in the atmosphere, and from there we are trying to make atmospheric predictions. That this kind of prediction is still a moonshot. What we can do is we can actually do a better science with machine learning today and with AI and data science before we get to the practice of healthcare. And this is where, for example, and next few slides, I'm just going to sort of skip and flash you. You look at the laboratory experiments and you identify the input-output dependencies. Maybe you do hypothesis formation, which could be automated. You could determine causality, and causality itself has many different variants and structure that allows you to construct networks of information networks that sort of gives you insight into what may be going on in the biochemistry level or in the biological level, not really giving a prescription, not really giving a solution, but giving you a better science. So for example, and this is not a solved problem yet, so I'm not going to give you something that says, look, here is this problem and here is the answer to it. What I'm going to tell you is how you approach the problem. So there is a condition called biliary atresia, which basically is seen in infants and newborns. Therefore, it is not really that much influenced by environmental factors. There is, of course, embryonic environment that might influence that, but it leads to basically prevention of drainage from liver, and it requires a surgery which is pretty painful and with mixed results. And so the question you ask is there anything predictive about knowing that there will be this missing bile duct in this information space we have? So it's the most common way you look at it is you have two sets of codes, biological codes. You have the DNA codes and you have the expressed DNA codes, which are the RNA codes, or the expressed DNA, which is in different tissues. So of course, since it happens in the liver, you want to look at the express codes, which is about 2% of the genome. So exome is about 2% of the genome. So you say, well, what are the differentiated genes between a normal and a biliary atresia patient, and then what are the SNPs that might be controlling the expression of these particular differentiated genes, and then can you sort of bring a correlation between them? Really, the amount of detail here is quite a bit, but what comes out is that you look at both the DNA and the expressed data, and from which you create network of genes and the mutations or the SNPs. So these numbers, small green numbers on top of the circles have genes, and the small numbers are the mutations, SNPs, that sort of affect that expression. And from there, you start to do a functional mapping, where you say this group of genes lead to fibrosis, this group of genes are connected to inflammation, this group of genes are connected to immunologic functions. And that allows you to sort of understand where the biochemistry of this work will be going, this particular disease may be going. Same thing applies to cancer. Same thing applies to a large number of diseases. Before we start offering solutions to prescriptive in field, we really have a very long path of doing that science. Now, that doesn't mean that the data science cannot be practiced or machine learning cannot be applied to real life scenarios. There are some very practical scenarios where it could be applied, but not for that kind of a treatment. So, for example, here is Ben Ismar, a colleague of mine at Data Science, a young faculty member, who looks at, for example, measurables like heart rate, resting heart rate variability, temperature, breathing rate, galvanic skin temperature, and all of these fortunately can be covered from a very simple sensor, just like the one I'm wearing on my ring, which has the sensors embedded into it. And then you start to build in a supervised learning way, a model of where you see these early signs, biometrics changing even before there are macro level expressions. This is fortunately very effective. And this is something that I think will become a common practice through our Apple Watches and rings and so on, where we actually are able to take better care of ourselves. We are also seeing the use of machine learning into understanding how brain works. It's very interesting. The machine learning architectures, especially neural network architectures, are inspired by a hypothesis about how brain works, and now using that insight into how actual real brains work. And this is where quite a bit of neuroscientists are looking at how humans are learning. And what we do is we train a deep neural network, and then we applied similar training to mice in a laboratory environment and try different algorithms and see the progression in the neural network versus the predictive model in the neuroscience area. And that is something that is sort of happening together, where the understanding of neural networks, and hopefully the math of neural networks, maybe in coming years to decades, will inform us how human mind works. We are also beginning to do macro scale, city scale level things. For example, here's my colleague Ilkay Altintas, chief data scientist of San Diego Supercomputer Center, who leads an effort on predicting wildfire spread. Those are common, unfortunately, in California, especially Southern California, but also quite a bit in Northern California earlier last year. And here, the number one problem is predicting where the fire is going to spread next. That is a function of where the fire started, which of course we don't know, so you have to guess. And then you have to know the ground conditions, the dryness conditions, then you have to look at the air flows, and based on all of those, you predict whether the fire is going to come to a particular neighborhood or not. And quite a bit of this predictive power has such a big influence that we had millions of people signed on looking at a particular street. Is my house going to be next or not? They're informing the firefighters, for example, where they should place their firefighting equipment. So we actually have a control center that works with the city and the county firefighters to help direct that. So let me just summarize this and then take the next 10 minutes to take an institutional view of data science as a subject area. This is a quote by Dale Gordon, which I thought was a little bit of a chutzpah, but basically, at least from a medical science point of view, but it is true that the role of data science is going to become much more significant in practice of healthcare in coming years. And so you go from symptoms to patterns to algorithms defining that. Philip, let's see, we have 10 more minutes, right?
We have a list of 4 questions so far, so it's up to you, but I'd like to keep it slightly below that.
Okay. All right.
So
let me
say 8 minutes. Yep.
Okay. Let me just give you some humbling thoughts first before we get to the next few things. One is that predicting contents of images is one thing. predicting human behavior is completely other. Whenever we come to social aspects, whether a person is going to be a good engineer or a good scientist, or from reading a resume, or a person is going to lapse into a criminal coming out of a parole board will lapse into crime again. The results are very, very mixed. I'm going to skip showing how mixed they are, but I'm going to tell you that they are worse than a random naive assessment by somebody who knows nothing about machine learning. And they can lead to lots of biases. So just relying upon such information to make predictions, or worse, using this information to influence people, as we saw in Cambridge Analytica, which fortunately doesn't exist, it leads to a lot of problems. And it is something that we need to be very, very careful about, and not become blind in applying machine learning to every single problem that could be formulated that way. Ultimately, data science is about connecting dots. It is definitely about creating new knowledge that does not yet exist, before it becomes utilitarian. It can lead to improvements in quality of life, and hopefully protect the environment around us. Let me take next couple of minutes to sort of tell you about the discipline itself. When we talk about discipline in academic sense, like this community of physical scientists and so on, you have a sense of what is good research and what is not good. You have a sense of what is justifiable in creating a conclusion, what is not. And that sense, by the way, varies significantly across domains. So the expectations are usually captured by community in their shared values and cultural expectations. When we come to data science, we are actually struggling with that question, because we have in the same unit social scientists, physical scientists, life scientists, each of which have a very different view of what makes a good research. So this is a community that will over time segregate from a generalist and a specialist. Right now, quite a bit of generalists are making a headway into it, but it is an exciting area. Number of areas, and I'm just calling it quantitative science, just to distinguish the role of data and the math with it. The questions that we are beginning to see in data science are significant. For example, how humans learn, I refer to that question. How machines learn, why does it work so well? Why does deep learning work so well? What is the underlying reason? Is it double descent? Is it some mathematical optimization that's going on? Causal reasoning, how do we discover and put to use the nature of causality from the observations? How do you mine data? How do you navigate uncertainty? Uncertainty is inherent in scientific endeavor. It is not so much inherent in computational endeavor, and that, by the way, causes cultural rifts and so on. And so the list goes on. This is an area that sort of is beginning to take a pretty strong role. What we are doing at UCSD is we launched HDSI, the Halijuolu Data Science Institute, about 3 years ago, a little over 3 years ago, a few months over. And we thought of it not just as another school or a department. We said it is something that connects with all the existing domains of knowledge, because the structure will come a bit later. What we do need to do, and this is where I want to echo Amitwa's the caution, that you need to be led by the domain scientists who are actually asking and answering those questions in different areas. And so before you get too much caught up into the models and methods and so on. With that, I want to come to the last slide and sort of summarize it for you as to what data science is. It is an area that is enabled by new platforms, new methods, new tools, new insights. And the discipline itself right now is a federation. of very different communities with very different cultures. Hopefully, they will melt together. And we have a whole bunch of our approach in terms of our academic programs so that the talent we are raising is actually very much connected to the domain scientists. And what I want to do is really thank you for your time and attention, at least staying with me as I faked my way through a team of scientists as to how a new philosophy, new love of knowledge is emerging, which is informed by real data. Thank you so much.
Thank you, Rajesh. That's a fascinating talk. Being a physicist, and rather naive physicist at that, I understood rather little of it, but that's my problem. That's why I'm attending the meeting. And I think it's okay for those of us that don't know what each other one does to be at a meeting like this and is to discover it. So I encourage some questions, perhaps to explain to a physicist what's going on, or perhaps some more interesting ones. I know that Dan has a few for us.
Yes, I got a few questions here on Slido. I'll start pick one out here. Let's see. How do we build trust in a ML model?
This is a very active area of research in trust. Trust and explainability go together. Things that we can attribute to. Now, I'm not an expert on how the trust is built, but from what I've learned from our faculty who are working in this area is trust is a function of explainability, which may be a function of very old concepts of controllability and observability in systems. Things that have causal relationships that can be discovered or inferred or imputed, except that the notion of causality might be more conservative than as we see causality in real life. In other words, it could even be a intersection between correlation and causality that drives a weaker notion of causality that allows us to estimate the level of trust one can have in the model. At the end of the day, predictability is a big component of trustworthiness. Unpredictability is not. And you know, there was a very interesting statement Peter made that some very simple examples where no amount of physics would give you predictability. And unfortunately, in real life, we are informed by physical world. Our devices are all very predictable, but our human behaviors are not. And we somehow think that we could through some modeling do that. There is inherent predictability, and there is probably Cook's theorem embedded somewhere that is about to be discovered, that there are some inherent limitations where the trustworthiness would not be achieved. So I don't know if I answer your question, but I'm just giving you parts of what I see.
Mm-hmm. That's great. That's a great answer.
Yeah.
Okay, so for those of us that are relatively new to this, this is a good, interesting question here. The pillars you pointed to are exciting, but there's so much out there that is daunting. That is daunting to know where to start. How would you suggest someone to get started?
That's a very good question, by the way, and that speaks to the heart of how we built Heliophysics Data Science Institute, and of course we'd love to see here. But I'm assuming that this model will take on. Here's what we have done. Every single student in our programs has to do a year-long project, and that year-long project is mentored by a domain scientist. So the best way to engage is to put the practice first. This is the problem I'm trying to solve. This is how I'm solving it today. So right now, for example, and that is the reason why we call it Heliophysics Institute, not a school or a department or anything else, because creating a territory forces you to define your identity, and that is a little bit too soon. So for example, we have faculty members who are jointly appointed with philosophy, jointly appointed with biology, computational biology, with pharmacy, with pediatrics. So we have people who really are literally informing their colleagues of what they're doing, because they have to, for their own promotion, for their own career advancement. So to answer your question, the best way is to actually not get so much caught up in methods. One of the biggest mistake people do is learn SciPy or some other toolkit, and then they start throwing it on every single problem they know. That is the worst place to start. In fact, what you really want to do is to take what you do to somebody who is developing those kits.
Yep.
Thank you.
So maybe it's a nice follow-on question to that. Here's an application. So we could think of things like flares. The question is, the network learns based on shown data. How can we improve the forecast of the unseen extreme event?
It's so there is a whole generation of techniques coming up. They call one-shot learning, or things that sort of like the way I refer to you, transformers or generative adversarial networks. They're really in early stages. Can they discover unknown physics? There is a theorem in computer science that ultra large scale networks always have some structure. In fact, they have something called a petal-like structure in data. So it is possible, and I'm just making a hypothesis here, that if you look at a large scale physical world, phenomena are connected to each other in some non-intuitive way, because obviously we haven't seen them, therefore our intuition will never get there. But learning networks could get there, because learning networks are able to detect features and patterns that may not be part of human experience. Our experience, our intuition is built upon what we see and what we experience literally, whether through our microscopes or through our eyes. And beyond that, it is some bunch of equations that sort of work very well with the last generation of physics. In the next generation of non-parametric model, it is possible that those phenomena would at least be pointed out early on. But it's not something that you would look for simply because you don't know what you're looking for.
Okay, interesting. Wow.
I'm not sure I answered that question, to be honest with you, to myself also, but that's my guess here.
So fascinating. Okay, let's see. So one more question. I'm not quite sure I completely understand it, but it says, could we design an AI-enabled cognitive picture to remove spectacles and/or other diseases? So I'm not quite sure what this question means, but
no, let me. So I think I understand. Maybe I do. There are now cognitive interventions happening, but we are, for example, the brain-machine interfaces are such that we could do kinetic motions, move things for paraplegics. So if I can think something to move an object, is it possible that there is a cognitive correction that can be done to a perceived image? My intuition tells me that probably you're better off playing with the transformer itself, the sensor itself, which means maybe something between the optic nerve and the brain itself before you get to the interpretation. But I don't really know. A brain is incredibly plastic. I know nothing about neuroscience myself. So the combination of those two doesn't help me, or you for that matter. But is it possible in some futuristic world for Hollywood? Yeah, I'm pretty sure. But we are in very early stages. One of the things that I really want to caution us more than I caution others is setting unreasonable expectations. We are going through a phase of irrational exuberance in machine learning.
okay. So that's it for the questions on Slido. Phil, do you want to? Thanks very much for a fascinating presentation and discussion. Phil, I'll let you wrap up the morning session. I think we're close to the end here.
Sure. Yeah, thanks to everybody. Thanks again, Rajesh. Thanks, Dan. Thanks to all the speakers and to all of you that have contributed questions this morning. And those of you that haven't, I hope you've enjoyed it. I, for one, am learning quite a lot. I'm learning more about what I don't know than I know, so that's a good thing. In the afternoon, in 1 hour and 32 minutes, we will begin the poster session. And Kendra Greb has kindly offered to advise people like myself who don't know how to get on that to get on that. Kendra, are you prepared to show us what's going on?
Well, I can give instructions, yes. Hi, everyone. For this afternoon's poster session, you can find the link very much the same way as you found this one through the Plenary Session tab on the website. We'll have a lightning session for 30 minutes where each poster presenter will give a brief overview of their poster, and that will be from 1 to 1:30 Mountain Daylight Time. And then at 1:30, you'll be able to join poster presenters one-on-one in the poster session gallery. So you'll want to select that tab, and then you can view each of the individual posters, learn in more detail about them, and be able to join them in chat rooms. So you can speak one-on-one with them. And that, I think, is what you need to know.
Okay, if anybody has any questions, you're welcome to, I guess, post them where you, I'm not sure I see the same screen as you, but if you have a question, post it and somebody will look at it and make sure that we all understand what we're doing. Again, thanks to everybody. I hope you have a nice break for an hour and a half. I feel bad for those of you in Asia at the moment. It's very late there. It's even quite late in Europe these days. So anyway, thanks to everyone, and we will get back to you. We will come back in an hour and a half. Thanks again.
Welcome everyone for this poster lighting session of second Eddy Cross Disciplinary Symposium. So as the session says, it's like a lightning session. So everybody will get opportunity here to present their poster for 2 minutes. So you can give nice overview and attract people to attend your poster. So as we start, Brian is here who will be assisting us. He will be running your slides, and then I will be giving you a time around after every 2 minutes. I will remind you about time, and you should be after 10 seconds or something, you should wind up within that. So all the best everyone here, and then we'll go ahead with the poster session. And first poster presenter is Neelam Bhosle. So Brian can start now. Okay, and yeah.
Yeah. Am I audible? Yeah.
Yes.
So I am Neelam Bhosle. I'm pursuing my PhD in Indian Institute of Geomagnetism, which is in India. So I will be presenting on the topic that is forecasting geomagnetic activity, that is DST index by using Kalman filter. So there are several modern technological systems deployed on the ground as well as in the space, which are highly susceptible for the geomagnetic field disturbances. So therefore, forecasting the geomagnetic disturbance well in advance is very important. So this work adopts the Kalman filter, that is data assimilation method, to forecast geomagnetic activity, that is DST index. So DST index is nothing but the disturbance storm time index, which measures the geomagnetic activity. So the data assimilation method, like Kalman filter. So one of the interesting thing about this data assimilation method is it uses the information obtained by real-time measurement while forecasting, and eventually it improves the accuracy of the prediction of the states. So there are two steps in the Kalman filter. One is the educated estimate of the state by using state dynamic function, and another one is the measurement of date by using the measurement function. So we have estimated a forecasted DST index by using recurrent state dynamic function, and this estimated DST index further updated by using real-time measurement of local disturbances at single observatory. So we have validated this forecasted DST index with true DST index, which we can see in the PPT. So here we have used the standard Kalman filter to forecast DST index. So Kalman filter implemented in this work offers an accurate forecast of the DST index with minimal error. So in future, we can use advanced Kalman filter to forecast DST index. So still we can improve the accuracy of the prediction of DST index. So this is the main idea, to use the Kalman filter to forecast DST index. So thank you.
Okay, next speaker we have Lindsay. Yeah.
Yes. Hi. Yes, my name is Lindsay Goodwin. I'm a researcher at New Jersey Institute of Technology, and I'm one of those Jack Eddy fellows. So I'm pretty happy to be here. But yeah, so the subject of my research is looking at plasma density irregularities in the upper atmosphere and connecting them directly to solar parameters that we have. One of the instruments that I'm using to do this is these things called advanced modular incoherent scatter radars, which you can see pictured at the bottom left, I think on your screen, I'm pointing the correct direction, at the bottom left, which is really just a panel of antenna. And these are very powerful instruments because they have a high spatial temporal resolution. However, they don't quite have a high enough spatial resolution in order to be able to resolve the small scale structuring that comes from solar wind changes that then create radio wave propagation effects. And that's really an important thing to look at if you want to do long distance communication. However, the technique that I apply in my poster that I talk about more within my poster, we're able to get a high enough spatial resolution to look at these small scale structures And in the middle here, we have a sort of plasmagram that shows this variety of scale structures that we have before and after a coronal mass ejection event. And here I'm just comparing the noon times, the regularity spectra that come from that. So the size of structuring that we have. And we see that there isn't much of a change before and after the CME. There's a little bit of a change, but not much. And so like the bigger question is like, do certain kinds of coronal mass ejections create these structurings that impact radio wave propagation? Is it something related to where the radar is on Earth that's changing the size of regularities that we're seeing? There's all these questions that we don't know, but there's some really excellent stuff if you come over my poster and talk to me more about it. Thank you very much.
Okay, great. Thank you for being within time limit. So next we have number. Anybody? Sorry. Okay, next we have Tamara.
So long-term trends in the ionosphere and their correspondence with solar and geomagnetic activity have been correlated with measured atmospheric parameters such as electron density, temperature, and other thermosphere ionosphere characteristics by several researchers in the past. Similar to geomagnetic indices, the local changes of the ionospheric weather are proposed to be graded by the W index at 4 levels of positive and negative logarithmic deviations of f of 2 is a characteristic density of the F2 layer. So the positive sign of this index refers to positive ionospheric perturbations, and the negative perturbations are indicated by the minus sign of this index. So we have performed an investigation of local weighted indices for ionospheric activity, and this is shown in the first figure of our poster, which is not shown here. So this is figure 2 actually, which is the focus of our poster. Here we consider the long-term trends of change of the average annual values of the range index. So subtracting the positive and the negative index to indicate variability, and compare them with the average annual values of the 3-hour geomagnetic Cape index, which is shown also in the same figure. So figure shown 2A in the top shows this comparison for 2 stations in the Northern Hemisphere, Moscow and Slough in the UK. And figure 2B shows a comparison for 2 stations in the Southern Hemisphere. So it follows from these figures that in the Northern Hemisphere, the gradual decrease of geomagnetic and ionospheric activity is observed, although the rate of this decrease of the geomagnetic Cape index, which is the slope of the fitting straight line, is significantly exceeds the rate of decrease of the ionospheric disturbances. However, there are opposite trends in changes of the geomagnetic and ionospheric activity in the Southern Hemisphere. So while the geomagnetic Cape index decreases, the ionospheric disturbance increases at Canberra and Port Stanley stations. So this may be due to the predominance of magnetographs in the Northern Hemisphere, which measurements are used to calculate the planetary Cape index. So as for the asymmetry of the behavior of the ionospheric disturbances in the Northern and Southern Hemisphere, there are different studies of this phenomenon in the literature, both in relation to ionosphere and magnetosphere. And so this study confirms these results and is associated with the difference in the orientation of the geographical and geomagnetic poles and the difference in the magnetic field in the 2 hemispheres.
Okay, thank you, Namra. Next we have Subhasis.
Hi, thanks, Ankush. Hi, my name is Subhashish Hazarika. I'm a postdoc with the Data Science at Scale team at Los Alamos National Lab. So this poster, as the title says, it's an unsupervised clustering and in situ feature tracking in a magnetospheric simulation model, right? So very often scientists kind of identify interesting or rare geomagnetic features or features of interest only while running the simulation at extremely high spatial or temporal resolutions, right? But talking from a data science or data analysis perspective, it's not always easy to dump this high volume of data and perform post-hoc analysis in an efficient and scalable manner, right? So this poster here is part of a bigger project that we are doing at Los Alamos, which is in situ statistical inferencing, where the idea is that you want to apply advanced statistical inferencing and statistical data analysis methods in situ or online. That is while the data still resides in the simulation memory. Right? So that basically gives you a way to perform this analysis online without having to store this high volume of data, which is cumbersome, and there are multiple problems with that. So one obvious problem is the storage size, but besides that, the bigger problem is the I/O bottleneck. That if you run at a high temporal resolution, you won't want to write out file at each and every time step, right? That consumes a lot of time. So that's the high level goal of this project. And here, what in the poster, we are presenting a specific case study of analysis with a space weather simulation model, where we are trying to first identify interesting features or clusters by doing unsupervised clustering using Gaussian mixture models. And we perform this offline on a medium resolution data set, try to understand what structures are interesting for the scientist. So once we identify certain interesting features or clusters, we can run the high resolution simulation models and then track the likelihood of seeing those probability features, right? That way you don't have to store the full data. You can just track the likelihood of those features. So please do come by my poster session to talk more about this particular work, as well as the in situ framework. If you're thinking of having some in situ analysis available for a simulation, I'm happy to chat and talk more about what we are doing out here. Thank you.
Thank you, Subhashis. So next we have Amy.
Hi, thanks. My name is Amy Kesey. I'm an associate professor at the University of New Hampshire. Today, I am talking about a large team project that we're working on. It's funded by an NSF EPSCoR Track 2 award. And it's a collaboration between people at the University of New Hampshire as well as at the University of Alaska Fairbanks. And what we are trying to look at is geomagnetically induced currents. So looking at during storm time, there's often all the changes going on in the magnetosphere and the ionosphere can induce currents, and those are likely to flow along long conductors on Earth. And sometimes that means they're going to flow along conductors such as the power grid or pipelines, and cause problems for our technology. It can cause power outages. It can also drive aging of the pipelines, and also affect some of the smart train systems. So we'd like to be able to understand the science of what's going on with these a little bit better, as well as potentially provide predictive models, forecasting for power grid companies and other technology infrastructure companies. So we're trying to use some machine learning models to do this. We're attacking this from a few different perspectives, looking primarily right now at solar wind data from L1, but also eventually wanting to incorporate some more data. Also wanting to be able to have some lead time in our forecasts to actually make them useful for the companies that might need them. We are looking at both mid-latitudes, that's sort of our New Hampshire focus, as well as high latitudes, which is the Alaska focus, but also more general what's going on as well. We also have an educational and outreach program called the Space Weather Underground that was started previously at New Hampshire, and we've provided some support for that, where we're having high school students build cheap off-the-shelf magnetometers and deploy them and look at the data. And the idea is to see whether a closely spaced array gives us more localized information, as well as to see if these cheap off-the-shelf magnetometers can be used for predicting rather than some of these higher end scientific instruments. So maybe we can get a closer spaced array for this kind of work. Thanks.
Thank you, Amy. Next is Natalia.
Hello, I'm Natalie Klein. I'm from Los Alamos National Laboratory. I'm in the Statistical Sciences group and working with these great collaborators listed here. This is on the same overarching project that Subhashish mentioned, but a slightly different methodology. So what we're trying to look at is in these space weather simulations, we want to identify earthward fast flows. And I apologize, I don't have video. So anyway, we'd like to identify these fast flow feature characteristics as the large simulation is running, potentially at a very high spatial and temporal resolution, so that we can actually track statistics of these features. So that's kind of what I'm showing on the left half of the slide. We have one particular feature we've identified, and then we're going to look at things like time series of its area, maximum plasma velocity, average plasma velocity, and so forth. And the real challenge here is that we found that it was difficult to automatically identify these features. So in particular, in the center, we're showing an elevation map of the plasma velocity at a particular time step. And you can see there's one very large feature in gray that we could easily capture with a large threshold value, but there are many other features in this blue area which are elevated plasma velocity, but difficult to capture with a single threshold. So we applied a topological data analysis segmentation method which is essentially using localized thresholding. And what we get from that in the right panel of this slide is on the top, we have our velocity in the x direction. And then on the bottom, we have the features that are selected by this topological data analysis. So you can see that we actually are able to isolate different features that are different kind of characteristic fast flows and actually separate those out from each other and then track what they're doing over time. And in the future, we'd like to look at how to use these different selected features in a statistical modeling framework. So if you'd like to come talk, I'm going to have a video session following this, so you can come by and chat. Thank you.
Thank you. Next is now Alexander.
Hello, my name is Alexander Kosovichev. I'm very happy to present these results at Eddy Symposium. I had opportunity to meet with Jack Eddy several times and discuss a basic mechanism of solar activity, and he was always interested what heliosysmology can help us, how it can help us to understand the solar cycles, the dynamic mechanism. And it took us 20 years of heliosysmic observations from 2 solar missions to get some understanding of what's happening inside the sun. So these measurements of analysis of 20 years of data revealed patterns of dynamo waves from analysis of torsion oscillations of the sun. So measure variations of differential rotation, calculate zonal acceleration, and then this evolution of these patterns showed us revealed the dynamo waves. And interesting that we already see that in this, so we understood that solar dynamo originates at the bottom of convection zone at 60 degrees latitude. And we already see actually the next solar maximum in the solar interior. That's an interesting feature. To understand better results, we developed a fully nonlinear dynamo model, and it explains very well the heliosysmic observation, tells the observation solar surface. And then we look further in this model and investigated how heliosysmic data can predict future solar cycles. And it turns out that it's indeed by measuring the flows deep inside the sun, we can predict the solar cycles 1-2 cycles ahead. So this is presented in this poster. Thank you.
Thank you, Alexander. Now we have next Eleni.
Hi, everyone. I'm Eleni, a PhD in the candidate in the National Kapodistrian University of Athens. I am happy to present a collaborative effort among all these co-workers. We have built a machine learning-based method for the binary prediction of solar energetic particle event occurrence. Our method is based on solar flare and coronal mass ejection observational data. We use SCP events identified in the CPAESS catalog. And we construct a high-level machine learning pipeline, including all stages of feature extraction and missing value treatment. And further, we apply a number of diverse classifiers to the problem, including logistic regression, multi-layer perceptron, support vector machines with linear and non-linear kernels, decision trees, and tree-based ensembles. We employ each classifier with a rather wide parametric grid and employ a randomized grid search, build 1,000 models of each kind, and then train and evaluate them in a self-consistent manner through a nested cross-validation scheme. Our experimental evaluation is extended and demonstrates that the proper setting is the imbalanced original defined by the observed class imbalance. We achieve good performance in generalization and perform post-hoc analysis on the results in order to derive meaningful explanations. I'll be happy to talk about this in the chat room. Thank you.
Thank you. So next we have Han Lee.
This is Hanli Liu from NCAR HAO. So this study is to look at robust climate responses to extreme solar minimum forcing and their hemispheric differences. So these are the main findings of the study. It's an extreme solar minimum forcing simulation. We find the robust climate responses. And also we identified the hemispheric differences in the interplay between dynamical and radiative processes. And in the study, we were able to quantify tropospheric surface responses and stratosphere responses that are mutually enhancing or offsetting. So the relationship between the top-down and the bottom-up mechanism. And we did this by driving the CESM vacuum with SSI TSI obtained from lowest solar activity possible, provided by MURAM MSG simulation, and also by comparing the ESM simulations with simulations under nominal solar maximum and minimum conditions. So yeah, if you're interested in more detail of this study, I look forward to talking with you in the chat room. Thank you.
Thank you, Hanli. So next presenter we have Rosissa. Yeah. We can't hear you. Can I'm not able to hear. Is everybody able to hear?
How about now?
Yeah.
From the Institute of Astronomy in Bulgaria, and as you see from this slide, the idea of this study is just to explore some new conditions, new parameters that will give a prediction for the confinement or eruption of the extreme solar flares. The study is done over 2 solar cycles, and the new parameters that are explored are the well-known coronal mass ejections, interplanetary radio bursts of type 3, in situ particles, protons for this case, and geomagnetic storms. So over the last 2 solar cycles, we have 172 flares. We analyzed, we did associations of CMEs and type 3 bursts, almost between 70 and 80% success rate. Much less are the SEPs and the geomagnetic storms, but there is a reason for that. And also the underlying active region configuration has been looked at. So briefly, the results, no much surprises here. We, like previous studies, the result is over 90% of the extreme solar flares are eruptive. The CMEs are the very good predictor for eruption, as previously known. What is the new here is that the type 3 bursts are a very good proxy for eruption. So in case you don't have data of CMEs, you may use alternative radio data from another satellite, alternative instrument. The surprise is that the underlying magnetic field configuration in terms of active region of the type alpha, beta, so on, is not a good identificator for eruption or confinement, because the 2 groups have almost the same conditions as type of active regions. So if you want some more information, you can read in this paper or chat later on during the session. Thank you.
Thank you, Lisa. So next we have Daniel.
Okay, can you hear me?
Yes.
Okay. Yes, so my name is Daniel Oko, and I'm a research scientist with the Center for Atmospheric Research here in Nigeria. So my interests are in ionospheric modeling, and I'm presenting this particular work, which I did in collaboration with some researchers at the South African National Space Agency. So we developed a 3D electron density model using cosmic radio occultation observations. So we get the data from the cosmic system, which mainly employs the technique of radio occultation to derive electron densities at different altitudes. So because the satellites, because of motion of the satellites, we're able to get the altitudinal profiles at different locations. And using these profiles, we trained neural networks that were capable to learn the variations in time and space, and also with geomagnetic and solar activity of the electron density. And that was a different work which is recently published. And so in this particular work, we're trying to use this model to study the variations or characteristics of the equatorial ionization anomaly, which we call the EIA for short. And so in this work, what we did mainly is to simulate our neural network model of electron densities to look at what altitude, so we can see in the data and method session the methods we use. So at different altitudes, we're able to locate at what height the double peak goes away, because we saw that as altitude changes, we get different variations, and until we get the double peaks, and the distance between these double peaks keeps decreasing, and at a certain height, it disappears completely. So we see this is something that
2 minutes
sorry?
over.
Oh, okay.
2 minutes
So
left.
so we're mainly looking at the variation of this apex altitude, where the fountain effect, where the plasma pulls the electrons to. And I will talk more with anyone that is willing or that has interest in this work in the chat session. Thank you.
Thank you, Daniel. So we have a next presenter, Andrea.
Hello, everyone. My name is Andrea Pricopi. I'm a fourth-year computer science student from Romania. And today I'm talking about the geo-effectiveness of coronal mass ejections. Coronal mass ejections that you've already heard of are powerful explosions from the sun's corona that sometimes can be geo-effective, meaning they reach Earth and disturb its magnetic field, causing what is known as a geomagnetic storm. And because there are still open questions about what makes coronal mass ejection geo-effective, this is a suitable task for machine learning. And this is what we're trying to do to predict whether a CME will be geo-effective or not using only solar parameters and machine learning. But this is not a trivial task, and first and foremost, this is due to the fact that we are dealing with extreme class imbalance, meaning that we have very little geo-effective events to learn from. And then because we have limited information available, mainly in terms of the number of available parameters. The machine learning models that we've tried so far are artificial neural networks, autoencoders for anomaly detection, and support vector machines. And our attempts to overcome the context-specific challenges include using balanced class weights, custom sample weights, oversampling the geo-effective events synthetically, as well as adding polynomial features. Our current results indicate that there's a need for a trade-off between the number of correctly identified geo-effective CMEs and the number of false alarms. But even under these circumstances, so far we've managed to obtain a true positive rate of about 72.9% and a true negative rate of roughly 97%. Most of the correctly predicted geo-effective events, as well as the false positives, are CMEs having the angular width and the central position angle values equal to 360, which is an interesting observation that I can talk to you about more if you join my session. Thank you, and I'll be happy to answer any of your questions soon.
Thank you. So next presenter is Sapna.
Hello, everyone. I'm Sapna, and I'm a postdoc at the University of Iowa. This poster is basically a subsection of the big picture work that we are trying to do at University of Iowa, which is to basically study the correlation between the solar wind parameters and then the drivers of atmospheric precipitation, and which are the most effective drivers. So what we are ultimately trying to do with this is we want to scatter this spatially, because we have a lot of data from this low Earth orbiting polar satellite called TOES. And we want to scatter this spatially and then be able to make predictions at each grid. But this is just the first step towards it. So what I'm presenting in the poster here is basically just a very simple classification model that seems to work for this kind of data. And so we basically find three different populations of electrons in the post data. So we will be studying what factors most effectively distinguish between the three of them. And if you look at the table here, we can see sort of a ranking of the different solar wind parameters. And so we find that the maximum velocity plays a key role in separating these populations, which is an agreement with a lot of the previous studies. So this is encouraging, and I guess from here, of course, the next step is to split this data into different spatial grids and make predictions at each point so that we can get a sort of a precipitation map. So thank you so much. That's all.
Thank you, Sapna. So next presenter is Tala.
Hello, everyone. Can you hear me?
Yes.
Okay. Yeah. So the topic of my presentation is Bayesian deep learning model for uncertainty quantification and prediction of geomagnetically induced currents, or GIC. And so this project is actually part of the MAGIC group project, which Professor Amy Kiss spoke of earlier. And basically what we're trying to do here is to quantify uncertainty when we are using machine learning model to predict space weather phenomenons like a GIC. And so uncertainty is basically situations involving imperfect knowledge, and it is inherent in like stochastic environments. And uncertainty quantification is basically the study of reliability of scientific inferences. So in the context of machine learning, uncertainty quantification is basically the estimation of the impact an uncertain input has on the model parameters and outputs. So it is relevant in the case of like space weather data like GIC data, is because GIC data is time series in nature, and the data distribution tends to change over time due to environmental variability. And also, although like data on solar flares, solar winds, etc., are like available, but historic occurrences of events like geomagnetic storms are scarce. So we developed a Bayesian CNN LSTM model, which is basically a form of a Bayesian deep learning model. And through Bayesian inference, we are able to get like posterior probability distributions for both the parameters as well as the output instead of like point estimates. So once we have like a probability distribution, we can place like a confidence interval. And this confidence interval ensures the reliability of the model output or the model accuracy. So it is to be noted that uncertainty quantification does not necessarily lead to like more accurate results, but it does ensure reliability or gives us confidence on the existing result. So I'll be presenting more during my video session and chat session. So I would be glad to talk about this more then, and hope to see you there. Thank you.
Thank you, Dala. So next is Ankita.
Yeah, hello. Okay, so I'll be talking about investigating the impact of space weather on habitability of exoplanets around M-Dot star as a case study using TESS mission. So the primary goal of TESS is to search for the transiting Earth-sized planet orbiting nearby and bright stars. So the main focus of TESS is to focus on detect the planets which are mostly flaring stars, and those planets are detected by using the transit method. So the transit method is the method in which you detect the exoplanets by studying their light curves. So, and by measuring the depth of the light curves, we can calculate the values, we can determine the size and radius of the planets. And by looking at the stellar flares in those light curves, we can calculate the values of the flare frequency and flare energy. So we have the certain, we have the Python based package, which is LTI Pony. And with the help of that, we can determine the values of flares. And we calculated the values of flare, which is coming around 10 raised to 37 erg and 10 raised to 34 erg for the largest and the second largest flares. And with the help of those values, we calculated the values of CME, which is coming around 10 raised to 22 grams and 10 raised to 20 grams. And from that, we can predict whether those values are essential to trigger the prebiotic chemistry. And like there are many other parameters which support life, like the distance from the host star to the planet, and the orbital inclination and other parameters. So we are looking into it, that whether the planet is habitable or not, with the impact of the flares and CMEs. Thank you.
Thank you, Ankita. And this is the end of session. And I thanks everybody for enlightening us about your work. And I'm sure many people might have got interested in your poster, and they will come to the poster session, which will be just followed after this session. Thank you for making it, for even in spite of having different local times. Okay, so I will hand over to Kendra if she has something information to give you. Thank you.
Hi, everyone. First, we had 3 poster presenters that we did not hear from today, but everybody should be available in either the chat or the video function. So if you log into the main website and go to the poster gallery button, you should be able to view the individual posters, and if you click on their individual posters, join their chats for the next hour and a half. We look forward to seeing you all there. Thank you.